Hi, welcome to Coding Bootcamp's YouTube channel. Subscribe now and join our live stream session later. See you.
Hey, how's it going? I'm Tom. I do voiceover for the video lectures at coding-bootcamps.com. You can follow them on social media and the sites listed in the top right. This is a quick intro for our Intro to the C programming language video series. So, who's this guy talking? I've been working with computers my whole life and started programming pretty young. Currently, I'm on my way to a bachelor's degree in computer science. My background includes Linux development, network programming, and game programming. C and C++ are my strongest languages, but others I know include Bash, D, C#, among others. There are no prerequisites for this class. I assume as little knowledge as possible coming into the series. So what topics do we cover? We get an overview of the C programming language, compiler directives, the C preprocessor, the basic data types that we work with in C, pointers and dynamic memory allocation and management, scary, I know. Macros, arrays, basic I/O formatting, program debugging and the tools involved in that, C's operators and expressions, and C's flow control. Alongside this course, there are 6 hands-on projects, and you can watch my live thought processes as I program a solution to each one after you do it yourself. So, what else will you get out of this? You'll get a basic understanding of C, the tools used to write C code, and the legacy and influence of C. Practices that are applicable to almost any programming language or discipline. Low-level memory management, getting into the details of how C and the operating system interact. And an understanding for how the computer handles data, those nitty-gritty details that some languages let you gloss over entirely. Follow-up classes include intermediate-level C programming with hands-on examples, and learn C++ programming by examples. Thank you for listening, and I hope you'll join us. Hi, welcome to an introduction to the C programming language. My name's Tom. I'll be your guide throughout this course. A little bit about myself. Computers have always been a part of my life. I've loved tinkering with them since I was a kid. As soon as I figured out how to program them, I've always loved that, and that passion has followed me throughout my life. I am in my last year of a bachelor's degree at a small CS-focused school called DigiPen in Washington State. I specialize in Linux development, network programming, and game development. C and C++ were core to my curriculum, and they are my strongest languages. This course has no prerequisites. I will be assuming as little as I can about your knowledge coming into this course. Additionally, I will try to avoid using any technical jargon, although some is bound to creep in at some point. There are always extra resources available to you to provide any clarity that you may need. So, for our first session here, we're just going to get an overview of C, and more broadly, an overview of computers in general. As a quick summary before we get started, C is operating system independent. We'll go into that. C has very specific goals and things it is capable of doing. And you might have heard of C before. It's kind of a cornerstone in the history of computing, and it has a pretty storied legacy. Over the course of all of this course, we'll be going over, among other things, all of the topics seen here. In this lesson in particular, we'll be covering memory, storage, the CPU, input-output devices, the compiler, and the general pipeline that the general pipeline from a programmer's thoughts and logic to the program that the computer can understand. So, to get this started, this is a computer, or rather an abstraction of one. There are many components to this, and there are many more components even than this, but as an abstraction, we can think of a computer as a CPU and memory, also called main memory, hooked up to a whole bunch of other smaller systems. The CPU's job is, I think the best way to explain this is consider a construction worker. The construction worker, the tool the worker has in his hands at any given moment is the CPU. It is the most readily available, but it also has the smallest storage space. So the worker can only hold one, maybe two things in his hands at a time. For anything else he needs, he has a tool belt. That would be his main memory. Memory is where values are temporarily stored, such that the computer can access them later if it needs to. Key thing to know, memory is volatile. That means if the computer loses power, either by getting struck by lightning or just being switched off, everything in memory is lost permanently. There's no way to get it back. If you need something to be stored long-term, you have secondary storage, also just called storage. For example, you've got your hard drive, a USB stick. In the long-lost days of the mid-2000s, you had CD-ROMs and DVD-ROMs. Or, well, not just ROMs, but CDs and DVDs. And this is where files are written to and information is stored for use between boot cycles of the computer. Give or take the depreciation of the hardware, if you turn a computer off, anything left on the hard drive or any other kind of secondary storage will stick around. Got input devices, that'd be your keyboard, your mouse, a camera, a microphone, a scanner, things like that. Anything that you use to give data to the computer. And on the other end of the pipeline, you've got output devices. So your speakers, your monitor, a printer, or even a network adapter. A network adapter kind of lives on both sides of this, such that you can receive data from the internet, obviously that's how you're getting this, and send data out to the internet. That's how you tell the computers that this lecture is hosted on that you want to see this. It's important to keep this abstraction in mind as you're learning, because it's pretty fundamental. The C language has some very specific goals. C code is meant to be abstracted from how the computer works under the hood. At the very, very bare metal, you have the machine code, the signals of ones and zeros that the processor uses to actually determine what it needs to be doing. This is arcane information known largely to the computer engineers, and the programmers shouldn't have to worry about it. It helps to know some about it, but you shouldn't have to know it. A level above the machine code is assembly language. Assembly language is a representation of the machine code in the form of mnemonics that programmers have an easier time understanding. Assembly is a scary word for a lot of people, but it's a tool like any other, and it's still used today. And finally, a level above assembly is higher level languages like C. C is kind of the lowest level, high-level language, if that makes sense. And what this higher level of abstraction does is it allows us to write programs that operate closer to how we humans think than how the computer thinks, with some concessions made where necessary. As far as writing modular code, C code, by and large, should be able to be plucked from its original context and slotted into other programs such that you can hook all the wires up right and get code from Project A to run in Project B with minimal interference. This isn't always the case, but it is a goal of C code. If you've ever seen a .dll file or a .so file for Linux users, that is a library of code that is a discrete module that can be plugged into other code. Hiding information, managing resources, and handling errors. The user should see as little of how the program works under the hood as possible. The program should manage the resources from the computer that it needs by itself, dispose of them when it's finished, and handle any errors as gracefully as possible, with ending the program prematurely being a last resort. Separating the interface from the implementation. This is something that we'll go further into when we go into what a C program actually looks like, but usually C programs are split up into two kinds of files: header files, or interface files, that give an outline of what the code is actually going to be representing, and then there's the implementation files that gets into the nitty-gritty of what exactly a particular function needs to do, what a particular constant is, and so forth. Writing code is part of a large team. Multi-programmer projects are a goal of most any language, but abstracted languages like C allow for programmers to more easily share their thoughts, and this enhances collaboration, obviously. And portable code. This goes back to operating system independence, which we will get further into later, but the short version is C code is C code, and C code should run almost anywhere. There is a pipeline between the programmer's thoughts and the program that actually gets written into, or rather the program that gets interpreted by the computer. The first step is a text editor. There are lots of text editors out there in the world. There's Notepad, there's Vim, there's Notepad++, there's Sublime, etc. All these do is they let you type ASCII characters from your keyboard and record them into a file on the disk. The compiler takes your source file, there's just any text file, and attempts to read through your file and turn it into machine code. If it cannot figure out what you've said, if you've made a mistake in your file, or if you've just handed it garbage, then it will output error messages and try its absolute best to tell you where it went wrong. This is not always possible, especially if you write particularly sloppy code, or if you hand it things that aren't code. If it is successful, it will produce an object file, which is kind of like a chunk of machine code without any knowledge of anything outside of its own context. For example, if you call the function printf in your code, the object file that comes out of the compiler does not know what printf is. Instead, it says, I need something called printf, please help. The linker's job is to take those messages and find out what exactly printf is, or anything else that you call from external code. Other object files will have the definition of printf, will have definitions of an exponentiation function, and so forth. The linker will cross-reference all of these and put them all together into one coherent file called an executable file, or a binary file. Not all binaries are executable, but all executables are binary. The loader will copy this information into main memory, tell the processor, hey, look here to start, and the processor's job from then forth is to run the program until the program says to stop. Some of you may see a problem with that. But at the end of this pipeline, you have a usable program, hopefully, with data that you can put in and usable results at the end. As a quick example, let's say we are trying to calculate a water bill. In memory at the start will be the raw code, the raw machine code for program. As part of the execution, we get some input, for example, the meter. Any data that is entered during execution also gets loaded into memory. Processor's job is to sift through all that data, do anything it needs to, and load the results into memory, which finally gets output into wherever it belongs. A file on the disk, output to the screen, a printer, even the internet. To jump topics a little bit, what is operating system independence? C is designed to work basically anywhere with an asterisk. If you can write a C compiler for your system, standard C code should run on it without a problem.
Thanks for watching. Feel free to add your questions as comments down below.
There is an exception in the form of operating system specific code, like for example, particularly abstracted Windows code will almost certainly not run on Linux or Mac OS or anything else. There are just certain paradigms that Windows wants you to use that are not compatible with other operating systems. However, for the most part, C is C, and you can run C anywhere you have a compiler for it. C is run basically everywhere. Quick history lesson. C, as I've mentioned, is a bit of a cornerstone in the history of computing. It had a handful of precursors, and there were plenty of high-level languages before C, such as B. But C has been the inspiration of basically every language afterward, except maybe like F#, which is more based on Fortran. There's a lot of information here. A couple of highlights are C++, which you've probably heard of. It's C with more features, essentially. And some things like generic programming, which lets you program for more or less any kind of data. C# and Java are very popular, more abstract languages that are based on the C syntax, and C++ is a particularly interesting one. C++ is generated by even higher level languages as kind of an intermediary language, and is used to basically accelerate compile time for those higher level languages by making C++ compile quickly, and by making the process of compiling to C++ quick, you in the end get a pretty fast compile time. So, in summary, we've seen what a computer is, how the computer deals with your program, the pipeline for getting your program onto the computer, and we've gone over some of the basic philosophy of the C language. Next session, we'll be going over the C preprocessor, compile time directives, what type def is, and a handful of other topics related to the preprocessor. There are live coaching sessions available on the website for software design, engineering, C and C++ programming, and so forth and so on. Thank you for joining us. Hello, and welcome back to our introduction to the C programming language. In this session, we'll be going over compiler directives, the C preprocessor, and getting a very brief look at the general structure of a C program. A quick recap from last time, we went over the design goals of C, we went over the legacy of C, and how its operating system independence works. In this session, we'll be going over use of type def, the preprocessor, and compile time directives. And again, a very brief overview of how a C program looks. So, the C preprocessor and compile time directives. If you remember the pipeline from last time between the programmer and a finished program, the C preprocessor is a step between the text editor and the compiler. They're generally lumped together because the preprocessor is useless without the compiler. The preprocessor modifies source code files before they get compiled. It can be used to do things like only compile certain code, like, for example, if you wanted to have multi-platform code, you could have Certain code get compiled for Linux, certain code get used for Windows, and certain code get used for other platforms while still sharing the rest of the code. It can copy-paste whole files into your source code. That's how you essentially add libraries to your source code, more or less. You can define constants and macros that can be used to inject extra code that can be a little time-consuming to type yourself or confusing to type yourself. You can give specific instructions to the compiler on a file-by-file basis. This is used to, for example, suppress certain warnings or errors from the compiler. Well, not errors, but suppress certain warnings, or give specific instructions on what to do in certain situations. And you can get certain metadata about a program, like what file a certain thing is called in, or what, or the exact date and time that a certain thing is run for logging purposes. These are not all of the preprocessor directives, but these are a lot of them. Include, as we mentioned earlier, can be used to copy and paste entire files into your source code. Define and undef can be used to define macros and constants, or remove those definitions if you need to use them for something else or just need them to go away. If def, if ndef, endif, and else, which are not those two are not listed here, are used for conditional compiling. As mentioned earlier, you can break code apart in some ways to make it so that it only compiles in certain ways under certain conditions. Error can be used to spit out custom compiler errors. File, line, date, type, and timestamp are little bits of metadata that the preprocessor can inject the code to grab whenever you need them. For example, if you are logging errors, you could get the file and line that the error occurred on. You can grab the down to the second or even less than a second time that something is run if you're trying to log just the activity of a long-running program. Among other things, there are a lot of uses for these. Pragma is used to deliver those very specific instructions to the compiler on a file-by-file basis. The pound and double pound macro operators are interesting, but they're very seldom used. And in the interest of time, I leave you to investigate these on your own. So, typedef. Typedef is used to allow you to alias type names. In the example given here, we have typedef. We have the name of a type, like, for example, unsigned char. And then we have the name we want to refer to this type as, in this case, byte in all caps. You can use this to rename types. You can use this to name new types using structs, which we'll go over later in the course. And in this circumstance, it's just used to give unsigned char a more descriptive name for the purposes we'd be using it for. In this case, it's a byte, because unsigned characters are just 1 byte in size. By convention, you usually want these to be all capital letters, but they're user-defined, and certain style guides can say you don't have to, and some people just may consider it as aesthetically displeasing. So you can 100% use a lowercase name. The only caveat here is your new name cannot be the name of any other type. This is a quick program that we can go over. You don't really need to worry about what this code does. It's more a demonstration of what a C program in general looks like. So we have a couple of preprocessor directives up here. The definition of main, which we'll go over shortly. Some variable declarations, a little bit of executable code, and the return statement. In this sample, it converts a given number of miles to the equivalent. In a sample run, we enter the distance, we enter 10, and it outputs 16.090000 kilometers. We can see the elements of the language that are used in this program in this admittedly a little bit messy slide here. So we've got preprocessor directives, standard header file, comments are marked by these /*/ blocks. You can see they can span multiple lines. There's a handful of words that are reserved by the C language, like int, void, and double. There's identifiers for library functions, printf and scanf. Special symbols used by the C language, so the equal sign and the asterisk here. Some punctuation in the form of commas and semicolons at the end of every line. That's something you'll get pretty used to. You'll find yourself texting a friend and ending something with a semicolon instead of a period. Happens to all of us. And there's more reserved words and special symbols. It's just generally what a C program looks like. The highlight of that whole ordeal is the main function. Main is what's called an entry point. The compiler looks for a function with a very particular name, particular kinds of arguments it takes, and particular return type, and says, okay, when I finish compiling and linking this, when we run the program, it's going to start from this entry point. It'll start from main. And so everything in your program all revolves around main. There are a handful of reserved words or keywords in the C language. These words have very particular meanings in the syntax of C, and they cannot be used as identifiers. Examples of this are int, void, double, return. Main is not a keyword, but it does have special properties in the context of being used as an entry point, so it can kind of be considered half a keyword. Standard identifiers. Identifiers all follow the same rules, but the names of functions and variables and constants in the standard libraries are generally considered sacred. You don't want to collide with them if you can avoid it. Examples here include printf and scanf, saw earlier. You can redefine them, but it's generally to be avoided. Your identifiers are anything you name. These names represent locations in memory, be that where a piece of data is stored or where a particular subroutine begins. The names you give them have to follow certain rules. They can only have numbers, letters, and underscores. They can't start with a number. They cannot be a keyword, and you, again, generally do not want them to collide with identifiers in the standard libraries. Very important to remember that C is case sensitive. So if you capitalize a variable name once, you have to capitalize it everywhere. And same goes if you put a capital in the middle of it. You have to put that capital in the same place every time. Here are a handful of valid and invalid identifiers, so it's easier to go over the invalid ones and say why they're wrong. So we have one letter, starts with a number, that's not allowed. Double, that's a keyword, not allowed. 2 times 4, the caps are fine, the star is not fine, the star is reserved. Cost per foot, dashes are not allowed, and Joe's, the single quote, is not allowed. Other than examples like this, you've got good examples over here, and there are a whole lot of different naming conventions that programmers will fight until the end of time over which one is best. Pick one you like and stick with it. As far as variables goes, variables are names for memory cells that data is stored in. This can be a little rough if you don't have a solid model of how memory works in your mind. So it's easier to think of them as just names given to values. In this example, we have miles and kilometers, KMS, that are both of the type double. So the general format is type of the variable, name of the variable, semicolon. We also have an alternative form right here. So type of the variable, name of the variable, comma, name of another variable. You can declare multiple ones on the same line. Assignment is something we did once in that other program.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
And you can see the line we did it on right here. Assignment is very, very important. What it does is it takes the value on the right, so whatever this ends up resolving to, and it puts it into the value on the left, into the name on the left, more or less. So in this case, what we do is we have a given number of miles and a conversion constant. We multiply them together, and we store the result of all of this in KMS. There are particular rules governing what you can do with the assignment operator that we will go more in depth in later. In summary, we went over a few key parts of the C language. We went over the C preprocessor, got a quick look at type def, and we got a general idea of what a C program looks like. Next time, we'll go over data types, constants, strings, character pointers, storage classes, scope structure, how scopes hide data, and data initialization. As always, on the website, there are live sessions for software engineering and C and C++ programming if you need those. And yeah, thank you for joining us. Hello, and welcome back to our introduction to the C programming language. This is our third session. Quick recap from last time. We went over the C preprocessor, compile time directives, use of type def, and we had a brief look at how a C program looks and the various parts therein. This time we'll be going over the built-in data types to C, a few qualifiers to them, constants and strings, storage classes, how scopes work in C, and how they hide data from each other, and data initialization. So, built-in data types. C has a handful of data types, each with a keyword associated with them. There are technically more than this, but these are the easiest ones. There's the int, which is short for integer. There's whole number. They are whole numbers with a valid range minus 32767 through 32767. In memory, they take up 4 bytes. They are signed integers by default, which means they can be negative, but there is a qualifier called unsigned that you can stick before an int, so you declare an unsigned int. That will make it so that it can only hold 0 and positive numbers. That all takes up the same amount of memory. There is the char, or the car, you might hear it pronounced. I tend to swap between the two. These are individual ASCII characters. In memory, they take up 1 byte, and if you need a character literal, you enclose it in apostrophes. Like in these examples here. You have a capital A, a C, a 3, and an asterisk, all of which just enclosed by apostrophes. The C compiler will interpret those as character literals. There is the float and the double. These two are very closely related. They represent real numbers. By that, they have an integral and a fractional part. You can look under the hood at how these are represented elsewhere. It is beyond the scope of this class, but it is useful information to know. They can be represented using decimal or scientific notation. You can use different ways to format output from the computer to get them in different ways. And the float takes up 4 bytes of memory, and the double takes up 8 bytes. This 8 bytes allows it to be double the precision, hence the name. Constants. You heard me mention unsigned earlier. There are other qualifiers to data types. For example, there's const. In C, there are two ways to define constants. You can use the preprocessor, like we went over last time, or you can use the const keyword. The preprocessor works how we described last time. You define a constant, and the preprocessor does a find and replace. Every time it, for example, sees the word length, it's going to replace it with the number 10 before it hands this off to the compiler. So here we would get length, replace it with 10. We see width, it just gets cut out and replaced it with 5. We get new line, it's cut out and replaced it with this new line character here. This is what's called an escape character. That / and a 1 or 2 characters after it denotes a character that cannot be typed normally on your keyboard, but is still important to be able to use for output formatting or for a handful of other things. On the other side of the coin, we have the const keyword. Consts can be of any type, but the key difference here is that the const variables are, well, variables. They have a specific location in memory. So this length here takes up 4 bytes in memory somewhere. What this means is that with some shenanigans, you can actually ignore the const keyword, meaning const acts more as a reminder to the programmer than as something the compiler and runtime will enforce. In general, it's a bad idea to do that, but it is technically possible. Besides those minor semantic differences, these two programs here, they both do the same thing. So, strings. We've seen characters. Strings are, under the hood, just arrays of characters. We'll go into arrays in more depth a couple of lessons from now. Suffice to say that an array is a collection of the same kind of data, just multiple of them. In C, and in anything that uses the C style of string, strings are terminated with a null character. That is to say, when considering a string, the compiler will run through that string until it finds a null character that's /0 or just a byte of all zeros, and at that point it will consider the string to have ended. We have a couple of examples here of 2 ways to get a string. So we have char greeting is an array of 6 characters, and it is defined using these curly braces as capital H, E, L, L, O, and the null character. A more concise and more human readable way to do it is to just char greeting is an array that is as big as it takes to hold the string hello. You can make string literals by surrounding them with double quotes, and when you do that, the null character at the end is implied, meaning that you don't have to specifically state it. You get a quick diagram of what this looks like in memory here. Another sneak peek, arrays in C start at an index of 0 and end at an index of their length -1. And you can see by the addresses here that the array is contiguous in memory, meaning it's all one chunk with everything right next to each other. The C standard library, which the string library you can include by using include string.h, has a handful of operations that you can use for parsing and manipulating strings. Strcopy will copy the second string into the first string, assuming there is space. If there is not space, strcopy will not say it failed, it is just liable that your program will crash because it looked at memory it's not supposed to. Strcat will do a similar thing. It will take S2 and just tack it onto the end of string 1. So, again, make sure that your arrays have the space to do that if that's what you need to do. Strlen will return the length of the string, not including the null character. The null character is always implied and never counted. So in this case, we would have strlen run across the length. We'd get 1, 2, 3, 4, 5. There's the null character. Our result is 5. Strcomp will compare string 1 and string 2. Technically speaking, it will determine if string 1 is lexicographically less or greater than string 2. The specifics of that are really not necessary to know. Just know that it returns 0 if the strings are the same. It will return something less than 0 if S1 is less than S2, or greater than 0 if S1 is greater than S2. For the most part, you care if it is 0 or if it is not 0. Strcr will look through a string and return a pointer to that string of the first occurrence of the character ch in string S1. As a quick example, let's say we pass this hello as S1 and the letter L as ch. Strcr will go through the string, say this isn't an L, this isn't an L, this is an L. I'm going to return a pointer to this character, which is basically an index into this array. So specifically, it'll return this address here. Strstr will do a very similar thing. It will look for a substring S2 in a longer string S1. If it finds one, it will return a pointer to it. If it doesn't find one, it will return null, if I recall correctly. So again, as a quick example, we pass this hello in as S1, and as S2, we pass in LLO. So we see this is not an L, so we move on. This is not an L, so we move on. This is an L. Next character in LLO is also an L. Okay, this is also an L, so we keep going. This is an O, and we have found the LLO. We're done. So we're going to bounce back here and return this pointer again. If that was a little complicated, we're going to go in depth into how pointers work in the next lesson. Storage classes. This is a useful trick. So a storage class determines how the C compiler and how the runtime manage the lifetime and storage of a variable. What that means is it determines how the memory is allocated and how long until the memory is reclaimed in the program. Like const and unsigned, they go before the type they modify. So what happens is you have the storage class, then any other qualifiers, and then the name of the data type. So the 4 types we have are auto, which is the default. It is implied whenever you declare a variable, like int amount over here. Technically, you can do auto int month, but I have never seen that done. Register, another one that's pretty rarely used, but it says that a variable should not be loaded into RAM. It should instead be held in a CPU register. In general, you're not going to need this because the compiler can optimize code better than you can. The compiler's job is dealing with the nitty-gritty of how variables should be stored, and it's just going to do a better job of that than any programmer can. Static. What static does is it instructs the compiler to keep a variable in existence during the entire life of the program. This can be done either in a variable scope or in the global scope. In the global scope, it is just always accessible, and its value is maintained however you change it. In general, it is mostly visible only to things that share a source code file with it. You can get around that using the extern keyword below, and we'll get to that in a moment, and there are examples in the next video. I know that I've been putting a lot of things off to that video, but trust me, I've written up some pretty useful examples that we'll go through line by line. Last one is extern. This is another signal to the compiler, but one that actually makes a difference this time. What extern says is, trust me, somewhere else in the code, in some other module.
Thanks for watching. Please like and share this video.
There exists either a function with a signature that looks like whatever I'm typing after, or there exists a variable with the name I'm giving you. Don't panic when I use this later in this file. Trust that the linker will find it. If the linker doesn't find it, then you've got problems, but the compiler will, in general, trust you when you use extern like this. So, scope and block structure. In C, scopes are defined by those curly braces that happen when you hold shift and type one of the square brackets to the right of the P key. Scopes can be nested within each other, and they determine how variables can see and talk to each other. There are 3 places a variable can be declared in C. There's within a scope block, which is called a local variable. There's outside of all scopes, which is called the global scope. Be careful when declaring things in the global scope, or specifically variables. Functions have to be in the global scope. And in the definition of function parameters, that's between the parens, which are called the formal parameters of a function. The way scopes hide data from each other is that lower scopes, meaning scopes that are nested deeper within those sets of curly braces, can see variables from higher scopes, but not the other way around. Or specifically, code in lower scopes can see variables in higher scopes. Let me see if I can find a way to explain this. If you have a variable in the global scope, and even though you can't have code in the global scope, let's pretend that you did for a moment. If you had code, executable code, in the global scope, then it would not be able to see any variables that are inside functions or inside lower scopes. Similarly, this is why a given function cannot see the variables inside any other function. We'll see why this is when we go into stack memory. Using global variables too liberally tends to result in sloppy programming with a lot of errors and a lot of data corruption. Use the global scope very judiciously if you, in fact, need to use it at all. Lastly, data initialization. This is different from declaration and assignment. In C, when you declare a variable, memory is reserved for that variable. But nothing else is done for that chunk of memory. The runtime just says, okay, you can have this chunk of memory and whatever's in it. Usually this means you'll be getting 0, but sometimes you can just get garbage. Modern compilers are pretty good at initializing to 0, but you don't want to rely on them for that. When you, in the same line as you declare a variable, you assign to it, like in the line down here, int I equals 0, this is called initialization. This tells the compiler, preserve this memory and load this value into that memory. This prevents you from getting any garbage data or any unexpected behavior. Again, initialization can only occur on the same line a variable is declared. If you don't initialize it, its value is undefined, and it's a good idea to initialize whenever you declare a variable, just in order to absolutely prevent as much undefined behavior as physically possible. One last note that's kind of unrelated. Assignment operators can be chained together. For example, this A equals B equals C equals D equals 10. Under the hood, this actually works from right to left. So what happens is this D equals 10 is resolved, then this C equals D is resolved, then B equals C, and then A equals B. And this would result in all 4 values being set to 10. Quick summary, we have gone over the basic data types of C, qualifiers, storage types, scopes, how scopes hide data from each other, and we have differentiated between declaration, assignment, and initialization. Next time around, we'll be going into the nitty-gritty of pointers, pointer arithmetic, dynamic storage, the size of operators, and pointers to pointers to pointers, oh my. I know pointer is a scary word for some of y'all. Don't worry, I will go as carefully as I can. As always, there are live coaching sessions from software design and engineering to C and C++ programming to whatever else you need, all on the website. Some extra resources if you decide you want to do some extra reading. And thank you for joining us. Hello, welcome back to our introduction to the C programming language. This is session number 4. Last time around, we went over basic data types, qualifiers, storage classes, constants and strings, scope, and we differentiated between data initialization, declaration, and assignment. As promised last time, I do have some examples written up, so let me just Alt-Tab to those real quick. We have 3 files that we're going to be working with here. The main ones that we care about right this particular moment are main.c and static.c. And so let's go through this. In main.c, we see we have a lot of extern declarations of functions that exist elsewhere in the program. These 5 in particular, 4 of them exist in pointer.c, 1 of them exists in static.c, and there is another one in static.c that actually doesn't have a declaration. And we have an extern declaration of an int stat int. These are all for demonstration purposes. In main, we call something called static main twice. And we have a couple of printf statements that are just dealing with printing values out to the screen. In static.c, we have int stat int equals 4. If I make this static, it means that this will exist for the entire life of the program. And it should be visible only to this file, but we will see about that. I'm learning a little bit here as much as you are, having played around with this a little bit. Static main has a static int scoped static, which can only be seen in static main. We print the value of scoped static, and we subtract 1 from it using the prefix ---- operator. And then there's getStatInt, which just returns the value of statInt here. So, if I open my command line here, let's see if I can zoom in on it a little bit. Do gcc star.c, so that's every C file in this directory. If I ls here, you can see we have these there. We gcc star.c, we -o intro.exe. We have a warning here. Implicit declaration of static main, so we didn't tell the compiler that we'd be using static main, but it's technically valid, it just doesn't think it's very good practice. And we have a linker error here, undefined reference to statInt. That's interesting. So if we see in static.c, we have a static reference, we have a static definition of statInt here. See what happens if we remove the static here. This is still in the global scope, which means it'll still exist for the entire life of the program, but let's see what happens. So, to run this again. This time that linker error goes away. So now we have extern int stat int, and this works just fine. Run this, so /intro.exe. And we get the output we expect. So the first time we see static main is called, scope static equals 7, and then we subtract 1 from it. We call it again, scoped static equals 6, proving that it still existed, it still referred to the same place in memory, and it actually got modified. Then we have the print out stat int lines, which works just fine here, and get stat int, which works just fine here. If we were to... Curious. Let's see what happens here. Here we go. Yeah, works just fine. So in this, we can see that at the global scope, static more or less restricts a variable from being seen outside of this file. And extern is more or less a reminder to the programmer that this is defined somewhere else, as much as it is a reminder to the compiler. Interesting little tidbit, with functions, calling them extern is implied. So if we try this, save it, clear, go back to the GCC command, undefined references stat ints, right. I did the thing. You can see nothing changed. This is because functions are always visible in the global scope. But similarly, you can make a function static, if I recall correctly, and now it won't be able to be referenced outside of that file. So you can use static to hide things between files at the global scope, and you can use it in a function to maintain a variable outside of when it's normally supposed to go away. So with that determined, let's get back to work here. This time we're going to be going into the nitty-gritty of pointers, how pointers work. And that says user, not use. Oh well. Pointer arithmetic, how dynamic storage allocation works, the size of operator, and double and plural indirection. So, what are pointers and why do we use them in the first place? Pointers in C are used in a handful of different ways. We can use them to create dynamic data structures that can't all be contiguous in memory. We can use them to pass variables around to different functions. This is called passing them by reference, as opposed to making a copy of them and passing them by value. We can use them to access information stored in arrays. We saw this last time with the strcchar and stir functions. And we can use them to reduce certain sources of overhead that results in our code being faster. It's a little difficult to describe how pointers work, but I will try the best I can here. If we have a variable int foo here, that foo refers to a space in memory that gets allocated for that variable. Whenever we use foo, we are just referring to that spot in memory and whatever is in it. A pointer is a variable whose value refers to some such variable or refers to some place in memory. On 64-bit architectures, pointers take up 8 bytes of memory. On 32-bit architectures, they take up 4 bytes. For larger, complex data types, it's often much faster to just copy a pointer to it and pass it along to a function than it is to create a whole copy of that data and pass it on to that function. And typically it's more useful too, because if you have a large data structure like that, in general you're going to want to keep it around and modify it directly instead of passing copies around and trying to use the assignment operator on it. So, how do we declare a pointer? What does it look like in our code? The way you declare a pointer is, it says here you have to put a star in front of the name of a variable. That is technically true, but not strictly speaking accurate. The star can go anywhere between the name of the data type and the name of the variable itself. So you can have int star space pointer a, you can have int space star pointer a, you can have int space star space pointer a, all of those are valid. Personally, the style I like to use is int star space pointer a, because the way it helps me keep track of it is the data type of pointer a is pointer to int. And having that all in one unit in the code helps me keep track of what's what. Different style guides will recommend different things, and different people will have different ways that they can remember what's what. The way that...
Thanks for watching. Feel free to add your questions as comments down below.
This is read is pointer A is a pointer to int, or pointer B is a pointer to void, which is a special case. This is often condensed or shortened into int pointer or void pointer. Void pointer is a special case, whereas int pointer specifically refers to a point in memory where an integer is stored. Void pointer refers to a point in memory where anything is stored. We cannot dereference void pointers, but we can pass them around and turn them into other kinds of pointers using casting. And we'll see an example of that later on in the scratch sheet. You can use the ampersand operator, which is the address of operator, in front of the name of an integer to get its address. We can see an example here. We have int x. We have pointer to int pointer underscore p. We assign 5 to x, and we just grab the address of x here. We don't do anything with them. Again, in later examples, we will actually do things with them, and it'll be interesting. We have an example of how pointer arithmetic works in this program. So, to get a quick overview, we declare a handful of variables, including pointers. So we have int var, int pointer, char var, char pointer, float val, and float pointer. Interesting that the naming convention changes here. We set int pointer to the address of int var, char pointer to the address of char var, and float pointer to the address of float val. We use printf to print their values as unsigned integers, and so we get them out over here. The numbers don't particularly matter because they're essentially random. They'll just be wherever there is free space in memory. We increment the pointers using the ++ postfix operator. And what this will demonstrate here is that pointer types are incremented according to the size of the data type they refer to in memory, which is why I told you all about that last time. So we see we have 2293300 here. After we increment it, we are at 2293304. We went up 4 bytes in memory despite only adding 1 to the pointer. The char pointer has a similar effect where we go from 2293299 to 2293300. We only increment by 1 because chars only take up 1 byte of memory. Floats being the same size as ints, we have the same increment here from 2293292 to 2293296 here. You can also add to pointers, which will produce similar effects. It is essentially adding a multiple of the size in memory of the data type to the pointer. So here we expect to gain 8 from last time, so that is correct here. We expect to gain 2 from last time for char pointer, correct. And we expect to gain 8 from last time on the float pointer, which is correct. So, pointers refer to locations in memory, but how do we work with what's actually stored there? That's kind of the important part here, no? This is what dereferencing is for. Putting a star before the name of a variable when you use it dereferences it, or depointerifies the value. We have the scratch work over here where we will actually show that. So this time we're going to set this aside, comment a few things out here. Uncomment pointer main. And let's go into what's actually in pointer.c. So there are 3 functions here that we care about. There is void increment, which takes in a integer by value. which means we get a copy of the value and not the same memory location. We add 1 to value, and then we throw value away. We do nothing of use with it. Increment pointer takes in an integer pointer, so we get an int by reference. We dereference the ref, and we assign it to whatever is already there plus 1. So we get to see the dereference operator in use twice in one statement here. And then there is dump array, which I will use specifically later on when we go into dynamic memory allocation, because one of the things that this function does is it allocates an array in memory, and then we fiddle with that array sum. So let's specifically focus on increment and increment pointer here. In pointer main, we create an int val equals 0. We create a pointer to val by taking the address of val. And then we try to run increment on val. As we mentioned last time, increment gets a copy of val here. So we add 1 to val and then throw it away forever. When we print out the value of val here, we expect to get 0. When we do the same thing, but we pass val by reference by passing a pointer to val, we expect to actually get 1 added to val. And when we print it out again, we'll see that that's true. And then finally, we call increment pointer by passing the straight up address of val instead of using a pointer variable for it. It's easy to remember that pointers are addresses and addresses are pointers. Then we print the value of val again, and we expect to get 2. Let's open up my terminal, clear it, recompile, gcc star.c-o intro.exe, run intro, and as you can see, we get the 0, 1, 2 we expect, and we get this output here, which I'll talk about what's going on there later. Back to the slide deck. Before we go any further here, we need to differentiate between stack memory versus heap memory, because we're about to go into dynamic allocation and the difference becomes important. Stack memory is a region of memory that the program in the C runtime will deal with on there automatically. Whenever you declare or define a variable, the memory for that is allocated automatically on the stack. Whenever you enter a new scope, meaning whenever you call a new function or go into a loop or an if statement, or just have a series of or if you just have a set of curly braces hanging out in your code, whenever you go into that, a new stack frame is created and pushed on the top of the stack. Whenever you leave that scope, that stack frame and anything in it is popped off the stack and lost forever. This is why lower scopes can see the variables of higher scopes, but not the other way around. When you're in a lower scope, all of the variables from the higher scope are actually still on the stack. They're just deeper in the stack. But when you're outside of that scope, there's nothing on the stack that represents those values. They just don't exist. They are pushed and popped off a stack data structure, so that is the last one in is the first one to get removed. And as mentioned, they are automatically managed by the C runtime. Heap memory is the alternative to stack memory. Heap memory is allocated dynamically at runtime. You have to ask your operating system for it. It's accessed exclusively by pointers to it, as opposed to the implicit references with named variables on the stack. and you have to borrow it from the operating system, which means when you're done with it, you have to give it back. And it's managed by the programmer in their code as opposed to automatically. So how do we manage that ourselves? We use dynamic allocation. One last quick note, the size of operator. Size of is very commonly used in the C programming language. I have an example of it on the scratch sheet. It is a compile time operator that is used to compute the size of whatever you pass to it. You can pass a variable to it, you can pass the name of a data type to it, and it will return a value, an unsigned integer, that represents the size of whatever you pass it in memory. This is how you can compute the size of larger data types. And it can be used on compound types like structures or unions, which we will go into later in the course. So, now that we know what size of does, how do we use that to dynamically allocate memory? There are two standard library functions that you need to know for this. They can be included using include stdlib.h or include standardlib.h. They are malloc and free. Malloc stands for memory allocation, and free is, well, free. Malloc takes in a single parameter, the size of the memory that you need. This can be assigned by you or computed, but ultimately, what happens is the operating system will see if it has the memory available to give you, and if it does, it'll return a pointer to it in the form of a void pointer. If it doesn't, it will return null, all caps null, which is a pointer whose value is 0. The null pointer is always invalid, and if you try to dereference it, your program will crash. So whenever you malloc, it's important to check to see if you actually got it, if you actually got the memory you asked for. I think I actually forget to do that in the scratch work, and I will correct that before we go into it. The free function takes the pointer that you return with malloc and deallocates the memory. You get no indication of whether this worked or not, but if you try to free the same region of memory twice, or if you try to free stack memory, or if you try to free memory that doesn't belong to you, your program will probably crash. If you do not free the memory that you get from malloc and calloc, the memory is lost when the program ends. This is what's called a memory leak. Memory leaks compound over time, and in the past they would exist until you restarted your computer. Modern operating systems are a little better about dealing with them, but it's still not a good idea to just let memory leak out willy-nilly. Special tools like Valgrind exist to detect memory leaks in the software you run with them. If we go back to the scratch sheet here, you can see we have right here, int pointer array equals malloc 5, so we malloc 5 ints here. We get the result and we cast it to an int pointer. This is just to remind ourselves what we're doing with it. And as I suspected, I actually did forget. So if array equals null, printf, we didn't get the memory, exit -1. I think that ought to work. And so now, this should never actually run because, well, my machine has more than enough memory, but it is still good practice. So, let's go here. Solve the little errors, run intro, and see what happens. So let's look at the code and look at the output we got. We know what happens with this 0, 1, and 2, but Why, when we call dump array, is there already a bunch of random values in here? When you allocate any kind of memory, but heap memory in particular, the memory is given to you as is. Whatever is already in there, the operating system and the C runtime don't do anything to change it. So,
if you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
When we call dump array the first time, we just get whatever we were handed. In these lines right here, we say array sub 0 equals 1, so we assign the first value of that array to 1, and we can also talk to that memory by dereferencing it and adding values to the pointer. So we assign to the memory we were given in two different ways. Called dump array again, and go back here, we see that we get the 1 and 2 where we expect them. The rest of the memory is still as is. Then we free our memory. Again, we get no indication of whether or not that worked, and we return 0 to exit cleanly. I mentioned that your program will crash if you try to free the same chunk of memory twice, so let's try that. Clear, go back to our GCC. Intro again. Huh, that's interesting. Should have crashed. I expected it to crash. I guess some runtimes can handle it and some can't. Do not bet on that behavior, ever. Let's see if this one can deal with having stack memory freed. So let's try to free val pointer. CC. Surprising, actually. In another environment I tested this on, the trying to do either of these actually crashed the program and caused what's called a segmentation fault, which is what happens when your program looks into memory it's not supposed to. And the way that works is the operating system allocates memory for its different processes and then keeps track of where each process tries to look. If the operating system doesn't care if you corrupt your own memory, but if you try to corrupt memory somewhere you're not supposed to be touching, then you are potentially endangering the processes that are running elsewhere on the operating system, and that's not okay. So what will happen is the operating system will stop your program's execution in order to maintain the validity of the data. Here's one that I am pretty sure will work. We try to free val itself, because remember, val's value is 2 at this point. So if we try to free the memory address 2, I expect bad things to happen. Pointer from integer without cast. Yeah, see, the compiler won't even let me do this without some shenanigans. Cast that to void pointer. Yeah, you see, the compiler really doesn't want me to do this, and I'm having to try to jump through hoops in order to even get it to work. In the interest of time, I encourage you to play around with this by yourself. So let's get back to business here. The last thing we really need to cover here is double indirection. We know that pointers can refer to places in memory, and they can refer to specific data types, but the pointers themselves are variables with locations in memory, and pointer itself is a data type. Specifically, we have pointer to int as a data type. You can have pointers to pointers, which allows you to have multiple levels of indirection, and you can actually extend this beyond just 2 levels of indirection if you really needed to. I can't think of a situation off the top of my head where you need it, but it is possible. You can have int pointer pointer pointer. In this example here, we have int I, we have int pointer, we have pointer to int pointer1, and we have pointer to int pointer2. This clear screen just empties the terminal screen. We say pointer2 is equal to the address of I. So now pointer2 refers to I. Pointer1, which remember has that extra layer of indirection here, now refers to pointer2. In this printf here, we get the value of whatever pointer1 refers to at the bottom level. So so we use the dereference operator twice, and we get the value we expect. That's 50, which is what's held an I. And in the second one, we just dereference pointer2 the old-fashioned way and get that 50. On this slide, we actually have a diagram of how that works. So I has a chunk of memory assigned to it. That memory is at address 2000, and we hold 50 in that chunk of memory. Pointer2 points at or refers to this chunk of memory here, and so we hold the value 2000 in pointer2's chunk of memory. Pointer2 exists at the address 3000. And pointer1 does the same thing. It refers to this chunk of memory and exists at the address 4000, holding the value 3000. Whenever you dereference a pointer, you actually just follow one of these arrows further down this chain. So pointer2 gets dereferenced and we get to I. Pointer1 gets dereferenced, we get to pointer2, which we can then again dereference to get to I. If you try to dereference I, you're going to have problems. Either the compiler will stop you, or if you do enough shenanigans that the compiler can't stop you, your program will just crash probably. Whenever I say a point, and again, if your program crashes, that's not a good thing if you try to publish it, but it is a good thing if you're trying to debug it, because it means that the operating system stopped you. It means that you've essentially gotten warning that you're doing something wrong before something actually went really wrong. So, in summary, we've gotten into the nitty-gritty of how pointers work. This is probably something you'll have to play with yourself, and something that you may want to reference the video on again while you're working with this. We've gone into dynamic memory allocation, how to stay safe when allocating your memory by using free, how memory is given to you, and how to manipulate pointers and essentially go frolicking around in memory. In the next session, we'll be going a lot deeper into how macros work, when to use macros in functions, how to inline common calculations, when to use a macro instead of a function, and how to debug using macros. As always, there are private coaching sessions available for software design and engineering and C and C++, among other things, on the website. Thank you for joining us. Hello, and welcome back to our Intro to the C programming language. This is session number 5. Quick recap from last time. We went over pointers, dynamic allocation, the size of operator, multiple layers of indirection, pointer and address arithmetic, flying overhead. Anyway, among a handful of other smaller topics. A little bit of a housekeeping before we keep going. Last time I brought up my Windows text editor of choice and my command line. I have been told this may have been a little too much too quick and to describe the tools that I've been using. The compiler I used is called GCC. The terminal shell I was using is called bash. And to get those on Windows, you need a utility called Sigwin. Sigwin is a free and open source utility that is a port of a handful of useful Linux tools over to Windows. When I'm working, Linux is my operating system of choice, but I've been working on Windows here because I figured it'd be a little more familiar for My text editor on Windows is Notepad++. It is very simple and very bare bones, but it has syntax highlighting, multiple tabs, other useful features for getting started, and it's quick and easy for if you just need to write a little bit of code. If you are on Linux, most distributions come with GCC installed by default. So if you're on Linux, you probably already have GCC. For people on Windows, again, Cygwin has the GCC toolset available in the setup tool. If you are on Mac, I don't know enough to make a good recommendation, in all honesty. I hear Xcode is the editor of choice, and I think that comes with the Clang or Clang compiler, but I don't know for sure how to get GCC. Clang and GCC operate pretty similarly, though, so you should be good to go there, honestly. The command I used last time to compile the 3 C files are GCC star.c -o intro.exe with spaces in between every major bit. You can see it right here. To break down what that does one word at a time, basically, GCC is just the name of the program, and everything after this is arguments to GCC. This star.c basically says, create a list of all files in this directory that end in .c. So any file whose last 2 characters are .c, put it into the list and copy paste that right here. So this is how I got all 3 of those files at once. This -o says that the next thing in the command line is the name of the file that I want you to output to. So in this case, I said that I want the executable file that GCC produces to be named intro.exe. If you do not specify this, what you get is an executable file named a.out. This can be problematic on Windows because Windows expects all executable files to end in .exe. On Mac and Linux, this doesn't matter because the way that files are set as executable in those is a matter of setting some metadata bits. All of this is gone into in more detail in an Intro to Linux development course that I will be recording later. Other useful flags for GCC are -wall or -wall, which sets all warnings to, which tells the compiler to output every possible warning if it finds them. -w extra or wextra, which does the same thing but more. So typically you want to use both of these together. -w error tells the compiler to treat warnings as if they were errors. I learned C using this. I recommend other people learn C using this, specifically because it forces you to write clean code. And it forces you to treat errors as what they are. The compiler telling you that you have done something wrong, even if it's not necessarily going to break your code. -ANSI and -pedantic are useful for learning raw basic C, but we're actually going to go into a feature in this slide deck that will disallow you from using ANSI at least, and probably pedantic. Basically, ANSI makes you conform to one of the original C standards, C90 if I recall correctly on GCC, and -pedantic makes the compiler a lot more aggressive about making you conform to that. So this session is going to be going into the nitty-gritty of macros, when to use macros, how macro inlining works, among a handful of other things you can see here. So, macros versus functions. As you've seen already, macros are a function of the preprocessor and not the compiler, which means that macros are just telling the preprocessor to generate code in place. If you've been paying attention, you'll be able to tell what's going to happen with this code over here. Just going to see this number and replace it with the number 10. See the number here, so we replace it with the number 10 in place. The function solution over here will semantically do the same thing. It'll just output the number 10 to the screen, but it has a bit more overhead here, and it works.
Thanks for watching. Please like and share this video.
Different under the hood. This number here is calling this number function up here. What that does is it means the runtime has to allocate a new stack frame as we enter a new scope here. Then when the runtime gets to this line of code here, well, it has to allocate memory for that 10 to take up somewhere, and pass that back to this printf here. So that's more memory that has to be allocated, and that's more overhead. So this code, despite doing the exact same thing as this, is considerably slower, even if modern computers are still fast enough that you're not going to notice a difference. It's still like on the order of microseconds. We see another GCC command line down here. This -e basically tells the compiler to pre-process it and then spit out the resulting source code to the terminal window to standard out. We see on the next slide what the result of that is. Above this line here, there's basically just a bunch of random declarations from standard io.h. Same goes for above this line here. So the main thing we care about is this chunk here, where we see the find and replace happened here. So the word number is replaced with the number 10. And in this chunk over here, we see the preprocessor didn't touch this bit of code at all. So why use macros? What's the point of having them in the language? Macros in general are not recommended anymore because they can cause a handful of issues. Modern compilers and modern C standards support the inline function qualifier as a kind of replacement for them. Some of the disadvantages of macros is that they're not type checked, so the type safety of C is just thrown out the window. They can be rough to debug because they're just simple cut and paste, find and replace. Macros aren't namespaced, so macros in one section of code can potentially affect others if, for example, that name gets used, or if you have another macro with the same name, that macro will work across all of your code and it can potentially cause issues. And macros can cause side effects because it's just copy-pasting code in place. If you're not careful, this can result in side effects and data corruption that weren't intentional. That said, the advantage of macros is that they can be type neutral with a little bit of effort. They're set directly into the code, so any function call overhead just goes away, as does any memory allocation besides things that are declared in that macro. So they can be faster, they just need to be used very carefully and very judiciously. In C++, it's possible to get around the type neutrality with templates, and in modern C and in all C++, I think. No, it wouldn't have been in C++ 98 because the inline thing was C99. So in recent versions of C and C++, the inline keyword helps get around the inlining and the function overhead. So what are macros used for? C macros do what all macros do. They take something small and they expand it into something big or longer. One reason to do it is, as you mentioned, it's performance. Because they're all in line, there's a lot less overhead to deal with. For an example of this, you can see the FD underscore family of macros. What these do is they deal with file descriptors. If I recall correctly, and I don't know for sure because I've never used them myself, But if I understood what I was reading, they are used to deal with synchronous use of files on the disk, meaning that you could have multiple programs writing and reading to the same file, and these macros can be used to signal, hey, I'm done writing to this file, it's safe to read from it now, or hey, there are people reading this file, maybe you shouldn't be writing to it right now. I kind of skipped over this, but it's actually pretty important. The inline function qualifier is not a mandate to the compiler, but is instead a hint to it. In general, this is a good thing. The compiler is smarter than you. This is a running theme here. The compiler knows or is able to calculate when the overhead of a function is insufficient to actually matter when it's generating the machine code for something. However, if you really want to make sure something is inlined, you've got to use a macro. The FD underscore macros are actually just bit manipulation under the hood. And while it's possible that you could write out all of the bit twiddling yourself, it can be a bit of a pain, and it's more confusing than it has to be. Assigning a name to these operations makes it so that it's a lot easier to read. And putting them in a function just adds overhead that's really not necessary. Macros can do some things that functions can't, like token pasting or stringifying stringifying tokens. Because the preprocessor runs before the compiler does, it can generate new variables for you. This can be a shorthand way to declare a whole lot of different functions at once. So what you could do, for example, is you could have a macro that has the skeleton of a simple function, but all of the like data type names would be replaced with the variable that you pass to the macro. Then later in the code, you call that macro with the name of whatever data type you need. So you could say generate function for int, generate function for float, and you'll be able to just have multiple versions of the same function. This is pretty similar to how C++ templates work under the hood, but not exactly. So, macros can help write portable programs. And this is part of what's called defensive programming. It's it's writing code while anticipating later hiccups. So if you need to write code that deals with multiple platforms, then it might be useful to have a macro to deal with certain differences between them. This will allow the nitty-gritty details to be handled in line while the majority of your code remains normal. Additionally, you can have macro definitions hidden behind if-def preprocessor commands, so you can actually change the macro depending on what platform you're actually compiling for. In this situation, we just see a simple add macro, which actually doesn't do what it says it does. But this is just a quick example that macros can be treated like inline functions. So this gets expanded into b plus c over slices, resulting in, let's see, in this case we get 16 over 8, so this will spit out 2 to the screen. So when do you use a macro instead of a function? Most of the time you want to be using functions or just writing things out verbatim, but in some cases you do need to use a macro. If you're doing things with token pasting, you need to be using macros. If you're dealing with line numbers or file names, or specifically line numbers or file names of your source code, for example, generating error messages, you need to be using macros. Dealing with things that aren't expressions, so that would be anything that doesn't resolve to a value. You need to use macros for that, because functions can only deal with expressions as arguments. Expressions or data types, but for example, how many implementations of the offset of command use a type name to create a cast operation? So let me see if I remember what this is. The offset of command will tell you, suppose you have a data structure in memory. In general, the compiler tries to make all of the data in this structure align nicely onto like 4 or 8 byte chunks of memory. And the offset of command can be used to determine essentially where a piece of data is relative to another one. But that's kind of complicated, and it's very situational, is what I'm saying here. There is a macro to get a count of array elements. It can't be done with a function because under the hood, arrays are all just pointers and pointer arithmetic, which is why you can use the subscript operator, those square brackets, when dealing with pointer arithmetic, as well as with arrays, because under the hood, arrays are just pointers. And we went over kind of type neutral / polymorphic code earlier. Generating functions with macros in C isn't true polymorphism, but it's about as close as you can get in C, without basically writing all of the features for C++ yourself. So, using a macro for debugging. You could see an example of having macros hidden behind ifdef here. So ifdef debug, we define debug print for x as printf x. So what this will do is in line, it will just call printf with whatever you pass, well, with whatever string of code you pass to this macro. If debug is not defined, debug print is an empty do while loop, which just does nothing. This is probably about as close to a null operation as you can get with a macro, without just defining it as empty. So, and then we end the if because the preprocessor needs that. We see an example line for this here, so we in parens pass this format string and these variables, and under the hood, this will just get replaced with call printf for these arguments. The extra parens are necessary because some C compilers don't support having variable arguments in macros. But it's sometimes worth trying without it if it makes it look prettier to you, but ultimately it's a matter of how much are you willing to tinker with it in the name of making your code look pretty. So, in summary, macros are useful tools that need to be used judiciously. Macros are most useful when you absolutely need something to be inlined, when you need to repeat something frequently without wanting the overhead of a function, or when you need to deal with certain meta details of your code, like line numbers and file names of your source code. Under most circumstances, you're going to want to use just functions, and if you're feeling like something really needs to be inlined, I recommend letting the compiler decide for you and just giving it the gentle nudge with the inline keyword. Where you put that inline keyword is before the data type of the function. So if you remember earlier how we actually up real quick. I can make a new file and send a view here. If you remember last time around when we made this static int here, the way you would use the inline keyword in C is you would just say inline func, inline int, inline func, just
Thanks for watching. Feel free to add your questions as comments down below.
void or int args or whatever kind of arguments you needed in here. That's basically macros. It's a little complicated, but ultimately there isn't a whole lot to go into with them, which sounds contradictory, and it kind of is. Macros are weird. If you need any of the source code from last time or from future sessions, if we end up using them, the source code will be uploaded to the course website, separated by session in which it was used. Next session, we'll be going in detail on arrays and how to use them, and how to deal with things like I need to do something on every element of an array. As always, there are private sessions for software design and software engineering and C and C++ programming available on the website. Thank you for joining us. Hello, welcome back to our intro to the C programming language. This is session number 6 of 10. If a quick recap of the previous session, we went into the nitty-gritty of how macros work and why you probably shouldn't be using them all that much. This time we're going to be going into detail about how arrays work. We've seen arrays before, but we kind of glossed over them, and I kind of just left you to play with them on your own. This time we'll be properly going into detail with them. So, again, we've seen them before, but just to make sure that the definition is fresh in your mind, an array is a chunk of memory that is dedicated to holding a whole bunch of the same kind of data. In particular, arrays are fixed size, so an array can neither grow nor shrink. Arrays have to all be of the same type, so you can't have an array where the first element is an int, the next is a double, the third is a character, the fourth is a pointer, etc. And arrays are generally used to give collections of data a name, as opposed to giving each individual part of that collection a similar name. This also allows this also allows the programmer to iterate through sets of elements of data in an array, using variables or using what are they called? Literals. Sorry. We've seen me declare arrays before, but just another quick refresher. The name of the data type, space, the name of the array. This space is actually unnecessary here, but can be used for style. An open square bracket, the size of the array, and a closed square bracket. This can be a literal, this can be a variable, but there are some caveats to using variables to declare the size of an array. This slide here says that this is called a single-dimensional array, but under the hood, all arrays are single-dimensional. You can have arrays of arrays, and those are often treated as though they are one contiguous set of, they're often treated as one multi-dimensional array, but under the hood, they're just arrays of arrays. Here we see a quick example where we have an array of 10 doubles. In order to read more complicated, declarations like this, there exists something called the right-left rule, where starting from the name of the variable, you go right until you can't, and then you go left until you reach basically a set of parentheses, and then you bounce right and left, and so forth. I don't think we go into any detail with that in this course. It's kind of an advanced thing, but it's something that you can look up yourself if you are curious about how that works. But following the right-left rule will give you a clear idea of what any particular variable is if you're having trouble reading the declaration or definition. So, initializing an array. You can initialize arrays in a couple of different ways. The first way is to use a set of curly braces. Inside the curly braces, you list out the values that you want to be in the array in order, separated by commas and spaces, like so. Actually, they don't have to be separated by spaces. The commas are sufficient. But the spaces are used to make it, readable to humans. The number of values between these braces cannot be larger than the number of elements in the array. If you decide not to explicitly state the size of the array, you do have to initialize it, and the compiler will give you exactly enough data to hold all of the elements that you list. So in this case, the compiler will say, okay, I see you want to make an array of doubles. You haven't told me how big it is, so I'm going to look into this initializer list here, and I see 1, 2, 3, 4, 5 doubles. Cool, I'm going to give you, that's what, 8 times 5, so 40 bytes of data for this array. And you can also assign to each element of an array individually using the subscripting operator, which is these square brackets here. So the square brackets are used both to declare an array and to access what is in an array later. We've seen diagrams like this before, but again, just quick refresher. We have a contiguous chunk of data here, enough to hold these 5 doubles. We list them in order, so we've got 1000, 2, 3.4, 7, and 50. And they are listed, they're numbered from 0 to 4. The first index of an array is always 0. And I am pretty sure I mentioned this in the lecture about pointers, but that's because arrays are pointer arithmetic under the hood. Whenever you're using an array, what the compiler says is take the address of the first element of this array and then add to it whatever is between the square brackets. So when you say array sub 0, the compiler reads the address of the first element in this array plus 0, which leads you to the first element. Addressing elements. Here we see an example of using the address, of using array addressing or array accessing to by using a variable to do it instead of a literal. In this loop here, we just go from 0 to 9, seeing how we have 10 elements in the array. We go from 0 to 9 and set each individual element to the array to I plus 100. If this looks a little confusing to you, feel free to skip ahead to the 10th lecture in the series. That'll be the last one, and that's the one where we go into detail about control structures like this for, if, while, etc. It might feel a little weird to do this in this order, but things all kind of... It's hard to find a particular order to teach things in C. Once it clicks, it all kind of just meshes together, and until it does, you kind of just have to pick orders to introduce things arbitrarily, more or less. So yeah, feel free to skip around, and feel free to go back and review if you need to. Stepping through an array, we see another example of using a for loop to essentially walk through every element of an array. In this case, we actually do it with a multi-dimensional array, or an array of arrays, using 2 nested for loops. we also see here that you can use a variable to name the size of the array. But if we look down here, we see that there is a caveat here. When you use a variable to make an array, you can't initialize it. This is because the size of that array isn't known at compile time. The compiler can't write code that will say for sure how much data needs to be allocated for that array. Essentially, it has to call something close to malloc under the hood. It's not exactly malloc, but it's pretty close. Let's see, was there anything else I needed to go over with that? I don't think so. I have an example of this in my Scratch sheet that the source code to which will be uploaded to the site, and towards the end of the lecture I will go over the example code I wrote. We'll compile it, we'll run it, and we'll see exactly what it does. Arrays of pointers. As I mentioned earlier, arrays can store any data type, and sometimes you'll want a collection of pointers. This might even be an array of pointers to other arrays, or it might be arrays of pointers to individual ints, or even a mixture of them because they're the same data type under the hood. So this is how you declare an array of pointers. Just int pointer, name of the data type, and you tell the compiler that it's an array. We have some sample code here. So we declare var as an array of ints. We have I as a looping variable, and we have a array of pointers to int named pointer with that is 3 elements wide. We see max declared up here, or defined up here. Then we walk through it. We assign each of the pointers in PTR to the address of a variable in var. So essentially, each element of PTR now points to the corresponding element of var. And the printf statement down here will show that to be true. We can dereference the pointers as we access them using the subscripting operator. Arrays of strings. Remember under the hood that strings are arrays of characters, with an extra space for a null character at the end. So similarly to how we make arrays of int pointers over here, we can make arrays of strings using arrays of constant character pointers. And we have an example here. So we have an array of strings here, so each individual element says hello world C is easy, but under the hood these are just pointers to character arrays. Passing arrays to functions. Fairly often you find yourself wanting to send an array over to a function, which is lovely and all, but C doesn't make that easy on you necessarily. There are 3 ways to try to pass an array over to a function in C. The first is by passing a pointer to the array. The second is by formally telling the compiler how big you expect that array to be. And the last is by just saying it's a generic array with no fixed size. The issue with this is that these second 2 ways are lying to you. When the compiler reads these, it says, oh cool, you're passing a pointer to an int, or you're passing a pointer to whatever data type. These 2 ways of having arrays as parameters to functions all instantly get turned into pointers to those arrays. This is for a handful of reasons. One is because in C, arrays are what's called a second-class citizen. Arrays are not given the same abilities that things like ints or floats or characters are. For example, you cannot assign one array to another. You have to individually step through the array and assign them, and assign each element one at a time. You cannot, I'm struggling to think of another example that isn't pass them as a parameter to a function, but, you know, here they are. So, the second reason why you wouldn't be able to pass an array as a parameter to a function is that we've seen before how parameters to functions are passed by value, which means that a copy of them is made.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
And pass along to the function instead of the original piece of memory getting referred to, unless you're using pointers. And this would cause a lot of overhead. The runtime would have to allocate all new memory. It would have to copy whatever's in the current array into the copy of the array, pass that along, and then basically just throw that memory away when it was done with it. It'd be a waste of memory. It'd be a waste of processor time. And ultimately, it would slow C down as a language pretty heavily. So instead, they just decided, nope, you can't do that. If you want to pass an array, you have to pass a pointer to it. If we move on a little bit here, under the hood, all of them produce the same result. We just went over this. Any information about the array is lost when you try to pass it like this, and because of this, you have to have another parameter that is the size of the array if you want to be able to index into that array safely. And so if you walked through this, you would check that you're not going outside of the size of the array. We see an example of this right here. Let's see. This function here just takes an array of ints, and you have to tell it the size of the array, and it will add all of the elements in that array up and divide by the size to return the average of the elements in the array. A couple of notes on dynamic memory allocation. We've seen previously that malloc takes in an arbitrary quantity of bytes to allocate. Because of this, we can allocate arrays using malloc. We just multiply the size of the data we need times the number of elements we want in the array, and malloc will give us one contiguous chunk of that size. When you're freeing memory, you do not need to worry about how much memory needs to be freed. The operating system keeps track of how much memory it passes and the pointers related to those for you. If you were thinking about this, it is good because something similar to this does come up in C++ in the form of, because C++ handles memory allocation in a different way to C, even though you can use the C method if you really want to. And because I couldn't find another place to squeeze this in, but this is a really fun fact to me, because arrays are all pointer arithmetic under the hood, you can make C do some really weird things with them. For example, there are 3 ways here to index into an array. You can have array sub 4 equals 2. This is the normal way to accomplish something like this. You can have 0 sub array plus 4, and what this does is, starting from address 0, I want to grab whatever is at the address of the array plus 4 times however big the data in that array is. Again, it's really clunky, it's really hard to read, and you should never actually do this in code you care about other people being able to read. And a similar effect is gotten by saying, starting from address 4, add the address of the array equals 2. Please, never actually use these bottom 2. This is an interesting little bit of trivia. So, multi-dimensional arrays. I mentioned earlier that arrays are all one-dimensional. However, you can have arrays of arrays. And you declare this in a pretty intuitive fashion. You have you tell the compiler how big the first array is, or it can be a little unintuitive. It depends on how you choose to read it. So the first thing you do is you tell the compiler how big one dimension of the array is, and then you tell it how big the other dimension of the array is. The strictly more accurate way to read this is the first thing you do is you give it the data type, the name of the array, and you tell it how big each individual array in the array of arrays is. And then you tell it how many arrays of this first size are in the larger collection. Again, it can take some practice to get used to reading things like this, but it will solidify the idea in your mind of what is actually going on when you tell the computer to do certain things. Similarly to how you access other arrays, you can use the subscripting operator twice. I can't point down there and it bothers me. So I'll just point in the general direction and wait for the thing to fade. Come on, quick as you like. No? There we go. So we would access column 2, row 0 by having a sub 0 sub 2, or a brackets 0 brackets 2. This is held in row major order, if I recall the naming convention correctly. And that means that rows are held together in memory and columns are separated in memory. So each individual array of this list of arrays is one row of this matrix here. Initializing two-dimensional arrays. If you remember how we initialized arrays before, this is a pretty simple extension of it, where you can start initializing one array and then initialize the other arrays as using the same syntax, separated by commas. So you can see the example here. We want one 4-element array of 0, 1, 2, 3, then 4, 5, 6, 7, and then 8, 9, 10, 11. Let's see here. The nested braces are optional because arrays are all contiguous in memory, meaning that essentially you are being given one long array that you get to treat like more than one. So doing it all at once like this is also perfectly valid. Accessing two-dimensional arrays, we actually went over that in the last slide, so I'll give you a moment to read this to double-check, but I don't see a reason to repeat myself. So, instead of going into a summary here over things we've heard already, I'm actually going to Alt-Tab into my Scratch sheet, and we're going to look at this code ourselves. So, I have included standard.io.h and string.h because I'm going to be doing some string trickery. Here is the dump array function that we have seen earlier, and let's go into main here. Array 1 is an array of 5 ints that I set them all to 0. I set them all to 0 by setting the first element to 0 and then letting the C compiler do what it does and assume that because I didn't list all the rest of them, 0 is fine. I have a size here, and so I have array 2 be an array of count ints, and I can define count as any integer. I have hello is a pointer to characters that are constant. So a string, and it says hello world. I get the length of hello world here. And I have an empty array of characters here that is long enough to hold hello world plus the null character. And so we'll be seeing we'll be seeing the one of the potential pitfalls of using a variable to make an array in a moment. So first thing we do, we set the last element of array 1 to 5, and we dump array 1 to the screen, and then without doing anything to array 2, we dump it to the screen. Real quick, let's clear this. GCC star.c o session6.exe. Again, this just takes all of that's the wrong character. Again, this just takes all of the .c files in this directory, and this tells GCC that I wanted to output the file named session6.exe. So compile this, works just fine. We can see that everything in array 1 is 0 until we set the last element to 5 here, but in array 2 we have random garbage in here. So when you get an array of a variable size, or you get it as is, just like when you're allocating heap memory. We'll go into everything this does in just a moment. So down here, we print hello copy before we do anything to it, and this is used to prove that that this character array will decay into a character pointer under the hood. So we're just passing this along as a character pointer. Similarly, we're copying the string hello world into this array over here and printing it again. We see here that the first time we print hello copy, it's again filled with random garbage. We just got whatever was already there when we started. And in fact, judging by how my no, that was incorrect. I was thinking that because my terminal let me select things from here, that we were actually getting a handful of invisible characters here, but that was incorrect because I can do that from anywhere on this terminal. I'm just used to other terminal emulators. Then the second time we get hello world just fine. These last 3 lines right here are examples of that crazy array subscripting syntax that I showed you in one of the later slides. So here we get the third element of hello copy, or the second if you want to say the first, the element at the beginning of the array is the 0th one. Either way, we get the first L in hello world. Here we get the first L in hello world in a different way by that's not right. By starting from address number 2 and then adding the address of hello copy to it. And the third time we do it by starting at address 0 and adding hello copy plus 2 to it. This is just proof that I'm not screwing with you. These 2 syntaxes are actually valid. Just never use them, please. And here is another chance to review the output. And in case you forgot, GCC star.c-o name of program. This source file will be uploaded to the website and should be accessible from the same page that this video is on. Before we go, next session we will be demystifying that printf function I've been using so much, going into how characters are encoded in C, dealing with standard inputs and outputs, among a handful of other things that are important to getting out the output you want onto your terminal screen. As always, there are private coaching sessions for software design and engineering, and C and C++, among other languages, available on this very site. Thank you for joining us. Hello, and welcome to our Introduction to the C Programming Language. This is session number 7. Quick recap from last time. We went over arrays and the details surrounding them, initializing them, stepping through them, passing them as arguments to functions, etc. This time we'll be going over file I/O, standard I/O, a brief note about character encodings, and we'll be demystifying the printf function that I've been using this whole time. So, in C, everything is a file. Or rather, everything that isn't just in the source code or in memory is treated as if it were a file. There are two ways that you can deal with files in C. There are the high-level functions that will pass you an abstraction called a file pointer, and you just pass this file pointer around to anything that will, or to whatever you need that will modify this file. And
thanks for watching. Please like and share this video.
Have those functions deal with it for you. Or there are the low-level operating system-specific options that pass you the file descriptor directly, and you use the low-level functions to deal with the nitty-gritty details of exactly how the file is manipulated. I recommend using the higher-level functions because they're a lot easier to use. The main thing for getting a file open in the first place is a function called fopen. This is found in standard io.h, as are the rest of these actually. And the signature is down here on my pointer here. So fopen takes a string file name. So this can be a relative path from wherever your program is being run, or it can be a absolute path that is the full path from the root of the file system to wherever the file is on the disk. And then it takes in a constant character pointer or a string mode. The modes are all down here. I'll go over them real quick in a moment, but this file pointer structure here. When fopen returns you this, it is not something that you're supposed to dereference like another kind of pointer. This is meant to be passed around, and the file pointer's job is just to hold the pointer in memory. Under the hood, all of the functions deal with the file pointer for you. So the modes that fopen can take are R, which will just let you read the file, and specifically these are hints to the operating system. I think you can violate these, but if you can, it's poor practice. If you can't, then the system is a little more bulletproof than I thought it was. Anyway, so R lets you open an existing file for reading purposes. If the file does not exist, it will hand you a null pointer. W will open a text file for writing. If it doesn't exist, it will create one. And if it already exists, then the program will still start writing from the beginning of the file, so you will lose anything that is in that file. A opens a file for appending. So it's basically, it opens the file for writing, like in W, and then it sends the file pointer all the way to the end of the file. So you can start writing from there. R plus opens a file for both reading and writing. W plus opens a file for both reading and writing, but it sets the file length to 0 first. So anything that so the whole file gets loaded into memory, and then anything you write will be the only thing that exists in that file. For regular W, it basically loads the whole thing into memory, and then you start replacing characters. So anything that you don't replace is left behind. And then A plus opens it for both reading and writing, lets you read from the beginning, and starts your writing at the end of the file. So it's kind of a combination of R and A. Standard input and output. It's a little difficult to describe these given the current modern paradigm of graphical interfaces, but in the old days, all we had were terminals, and there weren't many graphics. You just had command lines. And it's easier to understand what standard input and output are in terms of command lines. So let me actually just pull one up here real quick. So this is my command line. When I run a program on this, like say I'll just run cat for an example, and what this will do is it will just take anything I type here. So C is easy, and it will print it back out to the screen for me. It just echoes it back. There are two files in use with cat. The first is standard in. That is my keyboard, or more accurately, it's the terminal program itself. Whenever I type like this, the terminal emulator has whatever I've been typing stored in memory somewhere. And then when I hit enter, it realizes that I'm done and sends that line off to whatever program is currently running. And then the other file that's in use right now is standard out. Whenever the program cat decides that it needs to write something to the screen, it sends that off to the terminal emulator and it gets spit onto the screen like this. There is a third kind of file that deals with terminals like this, and that's called standard error. I don't have an excellent example of that right now. Let me just end that. But basically what standard error does is it prints out to the same place as standard output in these circumstances, but it does it in a different way. Standard output is buffered. What that means, let me see if that, there we go. What standard output being buffered means is that whenever a program tells standard out that it wants to print something out to the screen, standard out holds that for a moment and prints it out basically whenever it finds it convenient to do so. Standard error, on the other hand, is considered urgent. Whenever you print to standard out, it will dump the characters to the screen about as quickly as it gets them. The reason for this is because the error messages are generally considered more urgent than regular output. In a C program, standard in, standard out, and standard error are all identifiers for these standard file descriptors. They are defined in... they're not built-in keywords. I think they're defined in standard io.h. But you can use those whenever you would otherwise need a file pointer. There are two functions used for getting input from the keyboard one character at a time, and for putting characters on the screen one character at a time. The one for getting characters from the keyboard one character at a time is getChar. What getChar does is it reads from the current standard in buffer and returns whatever it gets as an integer. And what this means is, suppose I call getChar. I actually have a quick piece of code right here that'll just demonstrate this. So in this, I have the same line twice in a row. I just printf one character, and the character I get is from getChar. What will happen here is... I need to open up a terminal emulator here. Doop, bash, there we go. So, if I've already compiled this, and so we can see that the program is hanging here. It's not going back to the terminal prompt, but it is giving me freedom to type here. So, what will happen here is it's going to hang until I hit enter. It didn't get anything, and it's confused, so it's asking me for input again. Well, that's not quite true. It didn't get anything, and so it spit the nothing I gave it back out to the screen. if I do this again, what happens when I type multiple characters in is it will not ask me for input multiple times. Instead, it will print the first character out to the screen, and then because there is still information in the standard in buffer, it will print the second character out to the screen, and then everything after that stays in the buffer, but the program ends, so it just throws it away. Putchar will just take in a character and dump it to the screen instantly, or to wherever standard out is set to go. Putchar and getchar are fairly simple, but they're often a little too primitive to be used at scale, which is why we have other functions in the standard I/O library. Moving on, we have character I/O functions and formatted functions. Formatted output, like printf, is used for is used to make outputting things to the screen considerably easier on the program. Printf is a special kind of function called a variadic function. And basically what that means is it can take in any number of arguments of any different kind. And under the hood, there are special ways to deal with functions like that, but it's a little advanced for this course. Basically, you can pass printf anything, and so long as you give it a heads up, it'll know what to do. That heads up in this case is done with format specifiers. Format specifiers are a special kind of string that you feed to functions like printf that tell it what kinds of data to look for in the arguments. So you've noticed that whenever I was outputting a piece of data to the screen, I gave it a code that kind of looked like this. It had % and then a letter afterward. Those letters tell printf, I am giving you a particular kind of data here. And what it does is printf will note the order in the string that the format specifiers are, and it expects the kinds of data to occur in the arguments in that same order. So, if I go to the next slide here, I have a handful of basic format specifiers. The actual full list of format specifiers for printf is absolutely huge. I couldn't go over it in the time we have. I encourage you to look it up on your own and play around with it some. But the very basics are %d will convert it to a decimal number or an integer. %c will convert whatever data it's given to a single character. %s, it expects a C string, or a constant character pointer, to be passed to it. %f will output the data it's given as a floating point number, or a float or a double. By default, it has a precision of 6 digits, but some of the advanced things that you can pass to printf will let you play around with this some. There are special characters called escape characters. We've been over these a little bit before, but passing these escape characters to printf will have it print them in whatever way it knows how. As we've seen in my earlier examples, these format strings can have regular text in them, but it's this % symbol in front of one of these specifiers that will tell printf how to format things on the screen. If you need an actual % sign in your string, the format specifier for that is %%. And that's just a way for printf and anything else that uses a format specifier to be able to deal with that sort of thing. Here is a list of commonly used file I/O and character I/O functions, or rather their function signatures. For character input, we have fgetC, which takes in a file as an argument, and it just gets a character from that file. getC, which is very similar. getChar, which always gets it from standard in, and ungetC is weird. Basically, it takes the character you give it and pushes it onto the front of the file stream. It's kind of a way to put a character back where it came from when you're reading from a stream. It's very weird and very, very situational. Output, you have fputC.
Thanks for watching. Feel free to add your questions as comments down below.
Which just takes a file and a character and an integer character and pops it onto the screen, or pops it onto the file stream you give it. putC does something similar, and putChar does the same thing, but will only do it to standard out. String input, fgetS. This is what you're going to be using most of the time when you're getting strings from files. So you pass it a pointer to an empty string. You'll notice that it's not a constant character pointer, just a character pointer. Int n is the size of the buffer you give it in S, and stream is the file you're expecting the input from. What will happen is fgetS will read from the file until it finds a new line character, that's the /n, or until it gets to the end of the file, or until it reads n-1 characters. It leaves that last character as a guaranteed null character. So that way you don't risk having something try to read S later and have it not find that null character and go, frolicking off into memory it's not supposed to. Typically, what you want to do when you're getting input from a file is load a whole line into fgetS, process that however you need to, and use a handful of string to number conversion functions like a to I or a to f to convert those into integers, into floats, into whatever else you need. This is the safest way to deal with data from files. getS does the same thing, except it doesn't let you tell it how big the buffer is, and it only gets it from standard in. This is very, very not safe. Again, because getS doesn't know how big the buffer is, if you type more characters that it can handle, it'll just try to load them into memory there. And at that point, it's a toss-up between whether you've corrupted your own memory or whether you've corrupted someone else's memory. The operating system notices and crashes your program. String output at the bottom, you have fputS, takes in a constant character pointer, so a C string, and a file stream, just dumps that that string into the file stream. PutS does the same thing, except it just dumps the string you give it to the screen. It's like printf without any of the bells and whistles. Quick note before we end this off on character set encoding. There are a ton of different character sets and character encodings out there in the world. Usually when you're dealing with source code, you're dealing with ASCII. And when you're dealing with a terminal emulator, like you are when you're doing this kind of basic C programming, you're dealing with ASCII. However, there are situations where you will need non-ASCII character sets. Usually this is for pretty advanced projects that deal with like Windows GUIs and things like that. But there are other smaller situations where you might need them. C has built-in ways to deal with what's called a wide string, but they're not the safest thing to use because the way each platform deals with wide strings is not very convenient, and if you try to print a wide string to the screen, it gets undefined behavior. So generally, I advise staying away from those. There are libraries that exist to deal with non-ASCII character encodings, and they're fairly easy to look up. You can just look up the name of the file of the character encoding plus C library. C++ tends to have better support, but there do exist libraries for C. Under most circumstances, situations where you need non-ASCII strings are best handled using localization files. What those are is files that are full of strings used in your program that are translated to different languages and character sets. And what you'll do is you'll have code to recognize what string needs to be output here, and we'll pick a string from the localization file depending on what locale is selected in your program. It's a pretty niche kind of situation, but I felt it kind of important to quickly go over this sort of thing. In summary, file I/O is complicated, and it's difficult to go over in a 15 to 20 minute slide deck, but this should be enough to get you started, and it'll give you enough to play with and continue research on your own time. Next session, we'll be going into debugging. You'll be doing a lot of debugging when you're programming, especially with C. Because unlike newer languages with more complex runtimes, C is pretty close to the middle. C operates much like the computer does. As always, there are live coaching sessions for software design, software engineering, C and C++, among other things, available on the website. There are other courses that will be available soon. And thank you for joining us. Hello, and welcome back to our introduction to the C programming language. This is session number 8 of 10. A quick recap from last time. We went over basic formatted I/O, character set encoding, and the various file I/O functions in the C standard library. This time we'll be going over debugging your programs. So, first and foremost, what are bugs? Anytime you have unintended behavior in your program, that's a bug. They can come from any kind of mistakes in your logic or just mistyping something. I know I've forgotten to call functions before, and that's led to bad output. There are as many different sources of bugs as there are ways to program something incorrectly. Programmers aren't perfect, so bugs are going to crop up no matter what eventually, especially in more complex projects. So how do we track down where these bugs are, and how do we eliminate them from our code when we do find them? The easiest way to do it in C is just to use the printf function, honestly. You can have printf print out the current value of a variable as you run through your code, and that can often give you just enough information to tell you where something has gone wrong. Placing these regularly in sections of your code that seem to be having problems can be helpful to finding out what data is being corrupted or what's just being used wrong. And it doesn't require any extra tools. However, printf can't slow your program down for you like more robust debugging software can. And if you're not careful with it, having too many printf statements in your program will make it so that your terminal output is very, very flooded. And it can be pretty difficult to keep track of what's what if you use it too much. So if printf debugging isn't going to work for you, what about debuggers? Debuggers are tools that are used to slow down execution of another program, and typically they'll let you see the source code of that program too if it's available. Typically this is done so the programmer can watch as the program executes. Normally, you know this, your code goes too fast for you to be able to tell what's going on in any given microsecond. So debuggers will let you slow down and run through your code line by line, and sometimes it'll let you tinker with it while it's running. Set variables to certain values, tell it when to skip over certain bits of code, etc. Modern debuggers, including ones built into Microsoft's Visual Studio, there are debuggers included in a lot of modern IDEs, or they'll hook into other debuggers, or if you're working on a terminal in a Unix-like system, the GNU debugger or a spin-off called CGDB. These will all let you see the source code of your program as it's running, set breakpoints in the middle of your code, let you speed through the code you don't care about, watch variables in memory, among so many other things. Getting into the details of specifically how to use these tools is a bit outside of the scope of this because each of them operates a bit differently. In my opinion, GDB and CGDB are the most powerful options, and gdbtutorial.com that I've linked here it's a pretty good tutorial to get you up and running with it. What these kinds of debuggers are is something called a symbolic debugger. In non-symbolic debuggers, you'll usually just end up seeing the assembly code, which isn't particularly helpful for figuring out what's going wrong in the code you wrote, as opposed to the code the compiler made for you. And this, because we tend to think in terms of our own source code, being able to see the code as it's running is the preferred way of debugging it. In order for a symbolic debugger to be able to see the source code of your program, it needs to be compiled with the debugging information built in. In Visual Studio, this is basically always the case until you make a full release build. Even in release mode, if at the top of a Visual Studio window next to the little green play button, there is a drop-down to switch between debug and release mode. Even in release mode, you still have the debugging symbols compiled in. On GCC, you need to add the -G flag to your command line. Many IDEs will have tools that will do this for you. So if you're using something like Code Blocks or Eclipse, that probably has a plugin or built-in functionality to hook into the debugger for you. So a lot easier than telling you how to use debuggers is telling you how not to use them. Don't just step through your entire program one line at a time. Think about where things are actually going wrong in your code. Let it run normally until you get to the point where you actually need to see what's happening, and then slow down and watch things closely. This will save you a lot of time, and a lot of repetitive stress injuries from hitting the button over and over. Use the ability to watch variables. More helpful than just watching your code run one line at a time is the ability to query the value of any variable that's in scope. And a lot of debuggers will even let you modify those variables while the code is running. If something weird's happening, take the time to understand exactly what values are being held in memory, and that will probably give you a hint as to what's going wrong. Don't run your program start to finish if you don't have to. A lot of debuggers will let you set the next line of code that you need to execute. So if you're walking through your code one line at a time and happen to pass the section that's giving you trouble, and if you haven't solved the problem yet, you can tell the debugger to either start over if that's what you need, or just run through that bit again with the set next statement function. When you're using a debugger, turn off compiler optimizations. So that would be flags like -O2 or -O3 in GCC, and in Visual Studio that would be release mode. Compiler optimizations under the hood can make pretty drastic changes to your code, to the point of even like doing things out of order, or doing something called unrolling loops, where instead of actually going through a full loop, the compiler will see that you only do this 2 or 3 times, so it just copy pastes the code to do it 2 or 3 times. And because of these differences, these differences can compound, and if your compiler optimization is particularly aggressive, what you're seeing in the debugger may not actually be what code is running. So you do want to turn those off. Turn them back on once you've solved the logic error. If your logic is right, turning on the optimizations shouldn't change the output at all. And lastly, and most importantly, the debugger can't think for you. It just shows you some things you wouldn't otherwise be able to see. The most effective debugging tool is always careful thought. So once you've seen where the code goes wrong, how do you fix it? Like with that last point, careful thought is the best way to do this. Just think very carefully about what your code actually needs to do where the bug occurs, and contrast that with what's actually occurring. Sometimes the fix will be pretty.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
Obvious, especially for smaller ones, like just forgetting to call a function. I know I do that a lot. But sometimes it can be trickier. The worst bug I've ever had to track down took me like a week to fix. And I know there are a lot longer ones for people who have more experience in the industry than me. Break down your problem into simple steps and then write your code. It's the measure twice, cut once of programming. This was a pretty short one, in part because I can't go into detail about the various tools available, because each tool is going to be very different from the others. But we have gone over some quick principles about debugging and had a quick intro into debugging software. Next time, we'll be going over operators and expressions. We've been using those this whole time, but we're going to be going into detail about them. As always, there are live sessions for C and C++, as well as general software design and engineering available on the site. Thank you for joining us. Hello, and welcome back to our introduction to the C programming language. This is session number 9. Quick recap from last time, we went into the basics of debugging, and we didn't go into too much detail, but honestly, that's okay. It's pretty complicated, and each tool is different. This time around, we'll be going deep into operators and expressions, operator precedence, casting, and my personal favorite operator, the conditional operator. So, we've been using operators this whole time. Every time you've used a plus or a minus or a star or anything of that sort, you've been using operators. Most of these are fairly intuitive, I would hope. But some of them are a little out there, and they're not commonly used in the math we humans do every day. So, it's a good chance to go deeper into them. These 4 are fairly intuitive. You get your plus, which just adds the 2 operands together, your minus, which subtracts the one on the right from the one on the left, the star is the multiplication operator, and the backslash is the division operator. There is one caveat with this. If you are dividing 2 integers, you will get an integer. And more specifically, the division operator expects both operands to be of the same type. So you can't divide a float by an int or vice versa. And when you divide these 2 together, you will get the same data type back. So if you try to divide the integer 5 by the integer 2, you're not going to get the float 2.5 back, you're going to get the integer 2 back. You can also think of it as the value being truncated in this case. The percent operator is the modulo operator, which works pretty similarly to integer division. This is only applicable for integers. But instead of returning the integer quotient, you instead get the remainder, also called the modulus. The plus plus and minus minus operators are exceptionally common. And what they do is they will increment or decrement the the variable they're applied to by 1. This means it either adds 1 to it or subtracts 1 from it. Apologies. There are 2 versions of these operators. There's the prefix and the postfix. Both of these are valid ways to use the operators, but they differ in a subtle way. ++a will increment the value and then return the new value. A++ stores a copy of A in memory, increments the original one, and then returns the copy, which still has the old value. Under most circumstances, this isn't going to matter, because a lot of the time you're just doing the ++ on its own and not as a part of something else. But in the circumstances where it does matter, it's very important to know the difference. It can be the difference between your code working and it not working. So specifically, because of this, these examples are actually wrong. If you look up here, we say A equals 10 and B equals 20. A++ isn't actually 11. A++ will return 10, and then if you use A later, it will be 11. Same goes for here. A minus will return the original 10, and then if you use A later, it will return the 9. If you did ++A equals 11, that would actually be correct. Logical operators. This set of operators is used for Boolean logic. And what that means is these operators deal with whether a value is 0 or whether it is not 0. C doesn't have a true or false keyword. Instead, what C does is anything that is 0 is considered false when evaluating an expression for whether it's true or false. And anything that is not 0, so 1, -1, the maximum integer value, etc., all of those values are considered true. This will be important when we get to Boolean expressions and flow control in the next session. So, there are 5 main logical operators. There's the double ampersand, or the double and this is the logical and operator. If both the operand on the left and the operand on the right are not 0, then this whole expression evaluates to 1. If either one of these is 0, then the whole expression evaluates to 0. The opposite of that, well, kind of an opposite, is the double pipe symbol. The pipe symbol is what you get when you hold shift and press the / key. It's above the enter key on an American keyboard. And what happens here is if either A or B, if either the operand on the left or right is not 0, then the whole expression evaluates to 1. If both the left and right operands are 0, the whole expression evaluates to 0. Logical not is used to reverse the state of a Boolean expression. And this can be used on variables, it can be used on more complex expressions that are surrounded in parentheses, like so. And what it does is, if the expression that it's modifying evaluates to 1, it makes it 0, and if it evaluates to 0, it makes it 1. There are a couple of extra operators that aren't listed here because they operate a little differently. There's the comparison operator, which is A double equals B. And if A and B hold the same value, the expression will evaluate to true. So, for example, if you have A holding 1 and B holding 0, A == B is going to evaluate to 0. If you have A holding 1 and B holding 1, then A == B evaluates to 1. The opposite of that is a bang equals B, or exclamation equals. A common shorthand for the exclamation symbol is to call it a bang. And so this will evaluate to true if A and B are different, and it will evaluate to false if A and B are the same. These can be used to compare the values of pointers if you ever need to do that. And then there's these are a bit more complicated. The bitwise operators are part of the C language where the abstraction the programmer can use between what code they're writing and the actual ones and zeros in the computer, this is where that starts to break down. The bitwise operators operate on the individual ones and zeros of the data in the computer. So the operators we have here are a single ampersand, a single pipe, the caret symbol, which is, let me double check here. Yeah, that's the symbol you get when you press shift and type 6 on an American keyboard. And one that isn't strictly listed here is the tilde, which is the symbol you get when you hold shift and type the key to the left of the 1 on an American keyboard. The ampersand and the pipe do the same thing as they do in the logical operators. They are logical, they're bitwise and bitwise OR. And the caret is exclusive OR, which is not something we have an operator for in the logical ones. So there is a truth table here, which can help you figure out what an individual bit will do, or what two individual bits will do when subject to this operator. So let's run through that real quick. So we have P and Q. If we set P to 0 and Q to 0, P and Q is obviously 0, P or Q is 0, and P exclusive or Q is 0. The exclusive or is similar to the OR with one difference. If both are true, it evaluates to false. So this is used when you need one to be true or the other to be true, but not both. If we set P to 0 and Q to 1, we get P and Q equals 0, P or Q equals 1, and P XOR Q equals 1. If we set them both to 1, we get the values we expect. P and Q is 1, P or Q is 1, P XOR Q is 0. P as 1 and Q is 0 will do the same as P is 0, Q is 1. And you can see that in these two rows here. I have larger examples down here to show that these will operate on every bit of a data type at once. So in here I have given A and B a whole byte separated into sets of 4 bits. So we have A as the binary form of 106 and B as the binary form of 38. A and B, what you'll see here is that every bit that is set to 1 in both of the originals is set in the result, and everything that is either 1 or the other is set to 0. A or B gets the result, A or B will set every bit that is set in either of the originals. So you can see this second bit here is set in A, but not in B, but it's set in the result. A XOR B is a little more complicated. So if it is set in exactly one of the two original operands, it is set in the result. And if it's set in both or neither, it is unset in the result. So you can see here, we have the second bit is set in A, but not in B, and the second bit is set here. The third bit is set in both A and B, so it is unset in A XOR B. And then finally, there is a unary bitwise operator. This is the not operator, which works. It works by flipping the set bits. So if it is set, it is unset, and if it's unset, it gets set. So get 0110 1010 is changed to 1001 0101. And for convenience, I've added the decimal equivalents next to all of these. Typically, you're not going to be using the bitwise operators on numbers. You'll be using them on you'll be using them on sets of true or false flags. And they get condensed into one data type in order to make it easier to transport them all at once. So as opposed to sending a whole lot of individual ints or Boolean values to a function, you'll send one integer, and you'll just know in your program which bits are the result of which operations, if that makes sense. It's kind of an advanced technique, and you'll probably learn about it in later courses. Operator precedence. Operator precedence determine what order operations are performed in C. It's similar to when you were learning math in school, the PEMDAS. C has its own way of doing that, which is by...
Thanks for watching. Please like and share this video.
In large compatible with that. Operators can have an associativity of either left to right or right to left, which means that when there are multiple instances of that operator on one line, this will determine whether it starts at the rightmost instance of it in the line or the leftmost instance of it in the line, and then it will go left to right or right to left. The most obvious example of a right to left associative operator is the assignment operator, actually. If you have A equals B equals C equals D, etc., all the way up to whatever value you want to assign them all to, the rightmost one gets evaluated first. So D equals 20, and then C equals D, which is 20, and then B equals C, etc. It wouldn't work the other way around because all of the values would just be garbage until you assign them. Other than that, most of them are left to right. I have a link down here that links to a chart that gives you the list of operator precedences and the associativity associated with them. So, assignment and casting. C is very, very type safe. And what that means is C knows what data type is stored in any particular place in memory, and whenever it tries to operate on two different pieces of data, if they don't have the same type, the compiler will complain. Sometimes it will do it for you by converting, say, an integer to a float, but usually it will issue a warning when it does this. There is a special operator you can use called the casting operator. You give it a data type you want to convert something to, and it will do that to the best of its ability. You can cast pointers to different kinds of pointers, or you can cast arithmetic types to other arithmetic types. If you're feeling very, very brave, you can cast arithmetic types to pointers and vice versa, but don't. The usefulness of that is very, very niche. I can only think of one particular instance where it was necessary in an operation called the fast inverse square root, which was used in development of, I think it was a game called Quake. And this was necessary to allow the game to run as fast as it needed to. Square root operations at the time were very, very expensive and took a lot of time. Usually, the compiler will sometimes provide implicit type conversions, especially newer compilers, but it will issue warnings when this happens. Programs will sometimes do it when initializing variables, and if the necessary conversion isn't possible, the compiler will give you an error, and it will just not let you do that without explicit instruction to do so. Here's an example of the casting operator. So we have sum defined as an integer here, but we need a double here. So we cast sum to a double by putting double in parens next to the use of the variable. And then this one here is automatically converted because the first operand here is a double. This should produce a warning in the compiler. In more recent ones it might not, but in older ones it certainly does. Because the cast operator has pretty high precedence. I think the cast operator has the highest precedence, but don't quote me on that. I haven't checked the chart in a moment. If it does, it shares the highest precedence with a handful of other operators, like the function call operator. The value of sum in this example is first converted to a double, and then because the first one is a double, it sees the division operator and says, okay, I'm doing division with doubles here. Count is not a double, so I'm going to quietly convert it to a double so that the operation can work, and it will then assign this whole value here to the double mean. Certain data type conversions will result in loss of information. For example, if you tried to convert an integer to a character, you're losing 3 bytes of information there. And so the compiler will want you to explicitly say that you know what you're doing there. Similarly, if you convert from an integer to an unsigned integer, you're losing some information there because, well, you're changing what the bits in the you're changing what the individual bits in the data mean. And so if it is a negative if the integer stores a negative number, you're going to get some wildly high number on the unsigned integer. So the compiler will want explicit casts there. It's also useful to remind yourself and anyone else that's working on your code that there is a type conversion going on here. Last thing we'll go over here is the conditional operator. This is my favorite operator in the C language because it's really strange in how it's typed out, but it's astonishingly useful. Basically, the way it works is there are 2 symbols that you need to use in order to use this ternary operator. There is a question mark and then the colon. First, what happens is this expression here is evaluated to either 1 or 0. If it evaluates to 1, or, well, not 0, but usually that means 1 in this kind of circumstance. If it evaluates to 1, this expression is the value of the entire ternary expression. If expression 1 evaluates to 0, then expression 3 is the value of the entire ternary expression. This can be used as a very quick and convenient way to get a value out of a test. So say, for example, you need to determine if A and B are different, then you need the value of B. If they are the same, you don't care, so you just take A. Or some other situation. Maybe if A and B are the same, then you need the number 5, and if they're different, then you need the number 92. So you'd say if A equals B here, and then you'd put a 5 here, and then a 92 here. This can also be used as a quick way as a very terse, a very condensed way to have an if-else kind of thing. Where this differs from an if-else block is that if and else are statements that control the flow of a program. Those statements don't hold a value, they're just instructions. The ternary operator and the ternary expression, being an expression, holds a value. And they're useful in different ways. Here's a quick example of them, which determines whether we print out that a number is even or a number is odd. So the first thing this does is it gets a number from the user. You have to type in a number, and it will store that in num. Then we have our ternary expression here. So if num mod 2 equals 0, meaning that if you divide number by 2, it doesn't have a remainder, it will print out that the number is even. If the number is not evenly divisible by 2, it will print out odd. So you can see you can have function calls in these expressions too. Next session will be our last session. We'll be going in depth on flow control in C, which means things like if statements or loops that I've been using for a while here. We'll be demystifying those. And we'll have a brief moment about programming style, which is just how you type your code into your text editor and how you make it look so that other people can read it and that you can read it later. As always, there are live sessions for software engineering, software design, C and C++ programming. Thank you for joining us. Hello, and welcome back to our introduction to the C programming language. This is session number 10, our last session. Quick recap from last time. We went into the details for operators, expressions, Boolean logic in C, the casting, and the conditional operator. This time we'll be going into flow control in your program and have a brief bit about programming style. So, flow control. In C, flow control is how you change what parts of your code run under certain circumstances. If you just had to write one set of instructions that always ran every single time, you wouldn't be able to accomplish very much. A lot of things are very situational and conditional. And so, to start out with, we have the if statement. If what is a keyword in C, and so the syntax you can see right down here. So you have if, open parens, some Boolean expression, close parens, and a set of braces. If the Boolean expression evaluates to true, which means if the expression evaluates to anything that isn't a 0, everything in this set of curly braces will fire. If the Boolean expression does not evaluate to true, then everything between these sets of curly braces will fire. This else is optional, so if you don't want to do anything, if the Boolean expression is false, then you just don't include the else or these braces. Important to note, you don't have to have these braces if you're just going to fire one line if the condition is true. So, for example, if you're just looking for if something is true, fire one printf line, you don't need these braces. And many programming styles will not appreciate having those braces because it makes someone assume that something more is happening there, and it kind of just takes up space on the screen. So, the else is optional, always. The braces are optional sometimes, but the if bit here, you always need that. Motorcycle. So, the if statement is pretty simple and you'll be using it a lot. So, switch statements. Switch statements are probably the most powerful construct in C. And what they do is, an easy way to think about them is they're like a whole bunch of if-else statements chained together. Except that's not quite true. The main difference between them is, whereas a chain of if, else if, etc. statements, the conditions all have to be evaluated one at a time. With a switch, the expression is only evaluated once, and you can see the syntax here. The expression is only evaluated once, and then it just immediately jumps to where it needs to go. I have an example in my text editor that's a little bit more detailed than this, so let's go over there now and go over this. As always, this code will be available on the site. So here's what we got here. We include standard IO and standard lib.h. In our main, first thing we do is we ask for input. What I have here is just a character array to hold our input in. fgetS, I mentioned when we went over file IO. This is a safe way to get a string from a file while knowing that you're not going to overflow the amount of space you provided for it. And then what we do is we call a function called a to I. This is ASCII to integer. We pass it a string, so we pass it our buffer, and we get an integer back out. Then we switch over I. A few things to notice here. I skipped the number 2.
Thanks for watching. Feel free to add your questions as comments down below.
In my cases, so we have a set of cases here. And these are all of the different possible values of I that we will deal with. So I have 0, I have 1, I have 3, I skipped 2. You don't need every possible case. The numbers 6 and 5 are out of order, so they don't have to be in any particular order. And you'll notice that case number 3 has no break. After most of the other cases, I have a line that says break, and you can see by the highlighting that break is a keyword in C. What this break does in these circumstances is it exits the entire flow control construct. So when we get to this break here, we just exit out of the switch and continue to the next line, which in this case is this printf. If you don't have a break here, the slides say the break is optional, but that's not quite true. If you don't have a break here, what happens is something called fall through. Instead of stopping here after the printf, what happens is we just go to the next line here. So we ignore the case because that's part of the definition of the construct. This is the next executable line of code we find, and so we execute this line and then hit a break. So what happens here? Let's run through all of our cases real quick before I test this out for y'all. So if I equals 0, so if we type 0 into our program, we set I to 1 and break out. If it's 1, we set it to 2 and then break out. If it's 3, we set I to 12, then we printf falling through, and then we set I to 13, break out. If it is 6, we do nothing and fall through, because again, we don't have a break here. This is one of the examples where fall through is actually something you want. If you want to do the same thing for multiple cases, you can just type it like this, and you won't have a break, so you'll just fall through to the next one, so they'll all do the same thing. If it is 6 or 5, we add 2 to I. This is a special kind of operator called the addition and assignment operator, or plus equals, and this is equivalent to I equals I plus 2. Very, very useful, and something I kind of glossed over when we went operators because they're kind of special. And then, anyway, after we I plus equals 2, we have a break here. And then there's the default keyword here. Default is what fires if none of these cases are applicable. So if I is not 0, 1, 3, 4, 6, or 5, then the default case fires, in which case we set I to 322 and we break out. And then at the end, after we've done all of this, we just printf the value of I. If you remember, the %d means we're going to send printf an integer, Then the /n means there's a line break afterward, and I is the integer we're passing. So let me pull up my terminal here. Let's see, can I zoom in a little bit? So let's GCC it. Almost forgot. Cool. And now we will input a number for I. Let's start by just doing 1. And we get a 2 back. That's what we expected. Do it again. This time we're going to try 4. We get 13. Let's try 3. We get the falling through message, and we get 13 at the end, demonstrating the fall through I mentioned earlier. Switch over. Let's try 6 this time. We get our 8 back. 6 plus 2. 5, we'll get 7. And that is our 5 plus 2. And for our last one, I'm going to put something weird in. Let's say just that random number. Oh, I tried to pass that as an argument to the program. That was my bad. Let me try that again. And we get our 322 back. So that is a pretty neat little sandbox for you to play around with the switch statement in. I'll add some comments here explaining what these 3 lines do in more detail before I upload it, but that should be a pretty useful place to play around with it more or less consequence-free. Back to the slide deck. What do we got here? Next up is looping constructs. There are 3 main types of loops in C: the while loop, the do loop, and the for loop. What all of them do is they are designed to repeat a chunk of code over and over and over again until some condition is met, or rather not met. And basically what these all boil down to is the while loop, give or take some conditions. So the first one is the while loop. The while keyword is what's used for this. Then you open parens, you have some Boolean expression, so something that evaluates to, well, any number really, but it'll be considered false if it's 0 and true if it's not 0. Then you have a set of curly braces and some chunk of code in here, so you can have a statement, multiple statements, many lines of code. And so what happens here is, first, we get to the line of code that the while is on. We check the condition. If the condition is true, we execute everything between the curly braces. Then we jump back up here. We check the condition again. If it's still true, we execute that, and we continue that pattern until we check the condition and we find that it is not true. When we find that the condition is not true, we skip everything in the curly braces and just go to the next line. It's pretty simple, and you can actually create infinite loops doing this by just saying while 1, or while anything that isn't 0. Usually you're not going to want to do that, but it is possible to do. So, moving on here. Do loops. Do is very similar to the while loop, with one caveat. In a while loop, you'll notice that the condition is evaluated first. In a do loop, it's evaluated last. So what this effectively means is everything in the curly braces is guaranteed to fire at least once. So the syntax here is we have do, we have our opening curly braces, everything we want to do in the loop, and then the while condition bit here. Another thing to note is that while loops don't need the semicolon at the end, the do while loop does. And again, this is relatively intuitive. So we get to the do line, we go into the curly braces, we run everything that's in the curly braces, get to the end, we check the condition. If it's true, we jump all the way back here, run it all again. To the condition, and if we find it's false, then we just don't jump back. What we do instead is we just pass this and go on to the next executable line. Last one is the most complicated one, and ironically the one you're likely to be using the most. This is the for loop. The for loop is best explained as a kind of syntactic sugar around a while loop. Usually for a while loop, you're going to want to run things just a set number of times. So the for loop is here to kind of get all of the information necessary for that in one place. In the parens of a for loop, 3 different statements are expected. These are generally called the init, the condition, and the increment. They are separated by semicolons, so you don't put a semicolon after the last one here. And what this does is, first, when we get to the for loop, the init statement is run exactly once. Then the condition is checked at the top of the loop. If the condition is true, we run everything in the curly braces, and when we get to the very end here, before we check the condition again, we run whatever the increment is. So I have another page here that shows that these two are basically the same. So what we get here is we have the regular for loop syntax here. So for, init, condition, increment. And what happens here is we hit the init, then we go to the while condition. We do all our loop stuff, and at the very end we increment. Usually what's going to happen in the increment step is that you will run one of the plus plus operators. Like, for example, I can type that up here. So let's say int I for int I equals 0, I less than 10, plus plus I. Do something 10 times. This is the most common kind of for loop that you'll be using. You'll just set something to 0, say as long as that something is less than some number, plus plus I, and then you'll just do something however many times. You'll find yourself tweaking this a lot, so you'll find that this can actually be more or less anything. So say I plus equals 2. You could equals some other value, so let's just say j plus 5. You can do more or less anything in here. Similarly, the init can be multiple assignments, so you can say j equals I equals 0, j equals 4, I equals 0, something like that. And this condition can be any Boolean condition, so I not equal to 100. Do the same thing 100 times. The way you style all of these is largely a matter of preference and how effectively you can communicate the ideas that you're trying to program to yourself and other programmers. This is something I highly encourage you to play with on your own, and I believe some of the mini projects will be dealing with this directly. So, here. I mentioned programming style a few times over the course of this, and now we're going to get into the detail about it. Programming style is something that's personal to every programmer, and it is rule of law in among certain groups and like programming teams, companies, any other kind of organization that needs to be able to share code. Generally, the programming style is a set of standards put in place for how you type your code up such that people can easily read it if they know the style. This doesn't necessarily mean that they know what it's doing, but it does mean that they can generally look at it and get an idea of what's going on. There exist tools within text editors and IDEs to style code automatically for you according to whatever rules you put into place inside the program. My personal advice, and this is what I did when I was first learning to program, find a commonly used style that you like, something that looks nice to you, something that makes sense to you. Stick with it, and if necessary, use these tools to change to the preferred style of your organization. There are a handful of things that go into style, such as the curly brace style. You'll notice that in all of the examples here, they put the opening curly brace on the same line as whatever causes that curly brace to be necessary. But the style I use, you'll notice I put them on their own line. This makes it easier for me to read, and some people find this very difficult to read. Matter of personal preference. Other things, naming conventions. Different people will name their variables in different ways and make them readable in different ways. The fact that we can't use spaces makes it so that we kind of have to come up with a convention for this. So sometimes people use what's called camel case, where they'll capitalize the first letter of every word in a variable's name if it has multiple words. Kind of looks like the humps on it.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
A camel's back when it's capitalized. Snake case is what it's called when you have everything lowercase, but you separate the words by underscores. Hungarian notation is a kind of weird name for a kind of way to hint to yourself what data type any particular variable is. So, for example, a string will have a lowercase s in front of it. An integer will have a lowercase I in front of it. A float might have an f. Naming conventions are something that programmers squabble over constantly. So, again, find something you like. Line length. In the old days, terminals only were able to support 80-character long lines, and after that they would have to break and wrap it around. So some places and some people like to limit themselves to 80-character long lines before they put a break in themselves. Some people do 100 characters, some people just don't care, because, well, modern text editors will let you scroll as long as you need to. It's just find something that looks nice to you. Indentation. There are two main schools of indentation. There's using spaces, and then there's using the tab key. I generally recommend using spaces because it gives you more granular control. But basically, when you indent something in your code, you're using it to signal that this is part of a different chunk of code, part of a different scope usually. And so what people will do is, instead of writing everything on the innermost line, they will indent it by hitting space a couple times. I use 2 spaces, some people use 4 spaces, and some people use tabs, which are all 1 character. Usually a tab is about 4 spaces in width. I have my editor set up so that whenever I hit tab, it actually just inserts spaces instead. Ultimately, it comes down to whatever helps you work, whatever helps you be able to read your code, and whatever helps you be able to read the code of others. Programmers get into arguments all the time about which style is best and which one is readable. The style I use tends to be pretty close to how the original writers of C wrote their code. At least in one of the books I've read, I think. But all styles of C are valid, all styles of C are beautiful. Some of them are just more beautiful than others to me. Let's see. I think that's it. Flow control is a very fun thing to play with, and it's very important to learn how to use effectively in writing your code, because as things get more complicated, you're going to need those flow control constructs more and more. Code style is very personal, and programmers get into holy wars over them all the time. As always, there are live coaching sessions for C. And software design and engineering in general. Because this is our last one, I'll go over some other classes that are available on the codingbootcamps.org site. .org actually? Let me double check. .com, my bad. Codingbootcamps.com. So you'll have an introduction to Python, introduction to Java, introduction to Golang, introduction to Kotlin, with a more hands-on examples. Follow-up classes to this include intermediate level C with hands-on examples and C++ programming by examples. Hope you'll join me for those. Thank you for joining us. This lecture series was done by coding-bootcamps.com. You can follow them on social media in the sites listed in the top right. So, you've finished our introduction to the C programming language. We've gone over basics of how C works, the C preprocessor, fundamental data types and scope, pointers, dynamic memory allocation, they're not as bad as they sound, macros, arrays, I/O formatting, program debugging, operators, expressions, flow control, and I've walked you through 6 projects. Congrats, that's all we got for you. Follow-up classes to this include intermediate level C programming with hands-on examples and learn C++ programming by examples. Thank you for joining us. Hope I'll see you in the next one.